The Convair XFY-1 Pogo was the world's first truly operational tailsitter. It was also the fastest propeller-driven airplane in history. It was designed as a new breed of Navy fighter, a self-defense interceptor that could sit on the back of a ship and rise vertically to attack any threat. It had only one rival, the Lockheed XFV-1. Like the Pogo, the XFV-1 was built to meet the Navy's requirement for a tail-sitter combat fighter. It successfully flew in both the horizontal and vertical positions, but unlike the Pogo, it never attempted a vertical takeoff or landing. Both test programs were conducted throughout the early 1950s. By 1956, they'd been canceled. And yet the Pogo proved it could be done. It was the first tail-sitter to take off vertically, transition to conventional flight, and return to a vertical landing. This is the story of the brief but colorful career of the XFY-1 Pogo. To some, it is a success story. To others, just another misguided experiment. It's said that the Navy could never have used such an item. But if so, why did the program get as far as it did? And why is the concept being revisited? Naval aviation did not truly mature until after World War I. Under the leadership of Rear Admiral William Moffett, the Bureau of Aeronautics was established to guide the development of naval air power. The lessons learned in the First World War had shown that the fleet was best protected when in the presence of airborne guardians. Large flying boats with their heavy bomb loads proved a formidable defense against submarine attacks. The patrol flying boat would form the backbone of naval aviation, and as their range increased, they could extend the defense perimeter far off America's coastline. Flying boats clearly shared an affinity with the sea, but naval aviation was evolving. The Navy was looking for ways to tie aircraft closer to its ships. Small observation float planes were installed on vessels and launched by catapult. But a new kind of vessel would soon arrive, a new champion of naval warfare that would render these catapult planes obsolete.
The single float plane that the Navy had, things like the Kingfisher and its predecessors, the SC that came along behind it, were all designed to be spotting airplanes for the big guns on the fleet, the cruisers and the battleships, to determine where the shot was falling and correcting any errors due to windage or whatever. They could say up so many yards or down so many yards or so many mils right or left, and they could correct it and get the shot spotted in on the target. Well, with the demise of the gun as a primary naval weapon, as Navy to Navy, and the aircraft carrier being the primary combat vessel, there was no further need for the observation airplanes. Further, they could use the helicopter to do exactly the same job that the seaplane did, and with none of the difficulties that operating a seaplane provided. So the need for a seaplane or a float plane just stopped. It wasn't there anymore.
The aircraft carrier was literally a floating airfield, a mobile air base with which the U.S. Navy could extend its reach further than ever imagined. Naval aviation was maturing rapidly, and as World War II approached, it appeared that controlling the seas would depend largely on controlling the skies above. The age of the carrier aircraft had arrived. After decisive victories like those of Midway and the Solomon Islands, it was clear the aircraft carrier had changed the face of modern naval warfare. With this new spearhead of naval power, the U.S. and its allies began chipping away at Japan's Pacific Empire. Launching air raids, they wreaked havoc on island bases. In desperation, Japan launched a last-ditch effort to thwart the advancing Allied forces, the kamikaze attack. Suicide planes filled with TNT were sent to hurl themselves into the decks of carriers. With a direct hit, the damage could be devastating. It was a sobering thought. If the carrier could be sunk, so could all its aircraft. Despite the Holocaust, most kamikaze aircraft missed their targets. A few, however, did not. Navy planners began to question the wisdom of concentrating their air power on a single ship. Some called for dispersion. Others mentioned the term VTOL, or vertical takeoff and land.
The U.S. Navy had some awful lessons at the back end of World War II, tying their air power up in a relatively small number of flat-top ships called carriers, and they lost a few to the kamikaze aircraft. They wanted a self-defense fighter, basically, which could be based in almost any ship in a task force or fleet. And that was the move into VTOL. And the Navy, I think, the U.S. Navy, were the first ones to pursue this objective.
However, the Navy was not the first to consider the use of VTOL aircraft. The Germans, toward the end of World War II, designed a tailsetter called the Focke-Wulf Triebflügel. A ramjet was mounted at the tip of each of its 3 mid-body wings, which would spin and lift the aircraft like helicopter rotors. The Triebflügel was built as a fighter that required no runway, and it was intended to attack Allied bombers, which had already decimated Germany's airfields. Once airborne, the German tailsetter would fly horizontally, although it was never determined exactly how the transition would be made. To land, the pilot who lay prone would have to look over his shoulder, through the rotors and exhaust to see the ground. It was an awkward position, to say the least. Still, the German design did recognize that only the most powerful of engines would be sufficient to lift an aircraft straight up into the air. The Triebflügel fighter would never be built. It would have come too late anyway. Germany had already been brought to its knees under the constant pounding of Allied bombers. High above Germany, Air Force pilots learned how fast airfields could be destroyed. The idea was catching on. Perhaps the future of modern warfare lay in aircraft that can operate free of fixed airstrips. This is San Diego, California, as it looked just after World War II, cherished for its clear skies, warm climate, and coastal location. It is home to one of the largest U.S. naval bases, and it has always been a hotspot of aviation. It was also home to the Consolidated Vultee Aircraft Corporation, or Convair, which would build the first operational VTOL aircraft intended for the U.S. Navy. Here, during World War II, thousands of Liberator bombers and squadrons of long-range Catalina and Coronado flying boats had been built to help win victory for the Allies. Now, as America settled into the Cold War, Convair was building new aircraft, including the massive B-36 bomber, and new concepts were being developed. Under Project Hummingbird, the U.S. Navy had sponsored design studies for a VTOL fighter that could be installed on the backs of ships to protect naval convoys. In 1951, the Navy awarded Convair a contract to build such an aircraft. Captain Sid Sherby of the Navy's Fighter Design Desk was project officer for the test program.
We had the same requirements for it that we had for our seagoing helicopters. It had to be able to take a certain amount of crosswind, certain amount of deck roll, and all that. And that pretty much determined what the footprint had to be for it when it was sitting this way. And the idea for this was that it would take off vertically and gradually rotate forward and then go into normal flight and fly as a normal airplane. To land, it would come back at reduced power, and you can go through this transition and go to hover and then back and land. So all you needed was a fairly clear spot on someplace on the ship where there wasn't rigging or things like that would have a big enough footprint for this thing to come. And here you had your own interceptor.
The Navy contracted only one other company to develop a VTOL fighter, Lockheed. Both companies' designs would be built around the Allison T-40 turboprop engine. But Convair appeared to be one step ahead of the game. From the start, Convair elected to operate its experimental aircraft in the VTOL mode. For this reason, it received the first vertically running T-40 engine, which drove two contra-rotating propellers. The wing was a delta. This design concept would prove essential to making successful transitions between vertical and horizontal flight. At Moffett Field, California, the old rigid airship Hangar Number 1 was selected for what was officially called vertical taxi trials. From its 195-foot-high ceiling, Convair engineers dangled an enormous tether cable that was to be attached to the aircraft's nose. Once secured to the safety rig, the aircraft could rise to at least 100 feet and literally fly inside the enormous hangar. On April 29, 1954, the aircraft made its first tethered flight. By now it had a nickname, Pogo Stick, so dubbed for its ability to jump straight into the air. The Pogo's T-40 engine was actually two T-38 turboprops married into a single gearbox. It produced over 5,800 horsepower, and every bit was needed to pull the aircraft straight up by its nose. The cable rig installed above the propellers could either lift the Pogo up or slack off to let it back down. At the time, the team was unaware that the huge props were recirculating the air within the hangar. This caused terrific turbulence and often loss of control. Additional cables had been attached to the cruciform tips that went to powered drums. In the event of trouble, the pilot's cry was simple, "Catch me! Catch me!" And an engineer would then snap the cables taut to straighten the aircraft. The test pilot was J.F. Skeets Coleman. Coleman had been meticulous in his training for these tests. He had practiced in all types of helicopters to prepare for vertical flight. But nothing could prepare him for landing. In the vertical position, the Pogo seat lay on its back. While working the controls in front of him, Coleman had to look over his shoulder at the ground behind him. Similar to the German Triebflügel, landing the Pogo was a difficult maneuver. Hundreds of tethered flights would be conducted until the team was ready to take the Pogo outside for its first free vertical hover. Outdoors, the Pogo could fly without the ill effects of the hangar turbulence, but it would also be without the security of the safety tether rig. However, this did not bother Coleman. He was more concerned with the unnatural act of peering over his shoulder to land the aircraft. a problem that critics would later deem unacceptable. In November of 1953, Lockheed rolled out its VTOL experimental aircraft at Edwards Air Force Base for preliminary taxi trials. It was called the XF-V1. It was fitted with a special undercarriage beneath the fuselage for conventional takeoffs and landings. Although it used the same T-40 turboprop design, its engine had not been vertically tested, hence the need for conventional landing gear. The test pilot, Herman Salmon, was widely admired among test pilots, who knew him as simply Fish, and the XF-V1 would in turn be dubbed the Salmon, in tribute to its colorful pilot. Like the Pogo, the XF-V1 was designed as a tail-sitter, but its footprint was considerably smaller. The most obvious difference was in the wing design. Lockheed's aircraft sported stubby, straight wings, like those installed in the XF-104 Starfighter. The Pogo's larger delta wing was a Convair trademark. Its wingtips, in combination with the dorsal and ventral fins, made for a much wider and more stable footprint, especially for an aircraft that was going to be perched on the back of a rolling ship. The pilot's position was the same as that of the Pogo. To Herman Salmon, it seemed like a crazy way for a pilot to fly. Salmon and the Lockheed engineering team were unsure of the T-40 turboprop design. It was powerful, the most powerful propeller engine of its day, but they were convinced it was incapable of sustained operation in the vertical mode. They preferred to test the engine's performance and all the systems within the safety of conventional operation. As one engineer concluded, it was foolish to risk the pilot's life with an unreliable engine and an untested concept. Convair, on the other hand, was prepared to go all the way. On August 1st, 1954, outside the old airship hangar at Moffett Field, the Pogo engineering team prepared the aircraft for its first free vertical hover. The first of many defining moments for the aircraft and its pilot. The test had been scheduled for the early morning, for lower temperature and no wind conditions. In the tethered flight tests, the Pogo's engine had demonstrated power loss with rising ambient temperatures. Skeets Coleman, however, was more than confident. He had had a lot of practice mastering the Pogo's vertical handling capabilities inside the hangar. 60 hours of tethered flights, he thought, should be more than enough. Still, there must have been tension in the air. Not just for Coleman, but for everyone tied to the project. Convair executives, Navy brass, and of course the press were all going to be there to see if Pogo could truly fly. Not since the German Triebflügel had an aircraft been designed with engine thrust that exceeded the weight of the aircraft. Indeed, the Pogo's T-40 was pure muscle. The powerful turboprop needed no warm-up. Each of the two contra-rotating propellers were 16 feet in diameter. The two units had been selected to counteract the torque that would normally be produced by a single prop engine. Such torque force would have made control in the vertical mode impossible. Every bit of power was soaked up by the huge propellers. As soon as the turbine could be brought up to speed, the aircraft was ready for takeoff. The absence of warm-up was obviously a tremendous advantage, especially since the Pogo was expected to respond quickly to an attack on its ship. With a push to the throttles, the growling T-40 flexed its muscle and pulled the Pogo up by its nose. It had made this jump hundreds of times before in the hangar, But for this demonstration, Coleman had to prove how well the Pogo could maneuver in a free hover. In hover, the Pogo responded neither like an airplane nor a helicopter. For control, the prop's slipstream was deflected off the wing's elevons and the fin's rudders. Moving left or right was affected by the rudder pedals. Fore and aft by the stick. Easy enough so far, but if Coleman wanted to move off, say, 45 degrees, he would have to combine rudder and stick forces simultaneously and truly think about every move. It was very easy to become completely confused. Nevertheless, Coleman flew the aircraft like a pro, no doubt because of his extensive training in the hangar. Landing was still the most challenging act of operation. Craning his neck, he peered at the ground below him and eased the throttle back for a gentle touchdown. A howling success. It seemed fitting that this new breed of Navy aircraft should succeed at Moffett Field, so named in honor of the admiral who had championed the development of naval aviation some 30 years earlier. There was kudos for all, especially Skeets Coleman.
The pilot on this historic first flight of a vertical takeoff airplane was J.F. Skeets Coleman, Convair Engineering Test Pilot and Marine Reserve Officer. How did it go, Skeets?
Went swell, Dick. It was just the way we expected it. Of course, we didn't try to do too much, but everything went along fine.
I noticed that the operation was pretty much just straight up and straight down. Do you think you could have done more today?
Well, we could have done a lot more. The airplane was responding beautifully and just like we expected, but today we wanted to do just that, up and down.
Is it as maneuverable as a helicopter close to the ground?
Well, of course, we haven't investigated too far yet, but I think it's going to be much more maneuverable.
What do you think the future of the aircraft is?
Unlimited.
Indeed, to some, it would lead the next generation of Navy fighters. Convair considered the Pogo's first free vertical flight a triumph. But the next step would be the true test of a tail-sitter, a full transition into horizontal flight. The sole virtue of a tail-sitter, or any vertical takeoff aircraft, is that it doesn't need a runway. It can take off from virtually anywhere. It was thus necessary to build a ground transporter for the Pogo. If it could take off anywhere, something had to be designed to take it there. Convair engineers produced this special vehicle that could cradle the Pogo without harming the ventral fin, then transport it, and with hydraulics, lift the aircraft into the vertical launch position. One of the most important innovations devised for flight operation was the adjustable pilot seat. It was designed to rotate about 20 degrees forward during the transition from horizontal to vertical flight. Without this rotation, the pilot would literally fall out of the airplane, regardless of how strong he was or how tight the shoulder straps might be. This only added to the complication of flight control. As Coleman would soon learn, making the transition for vertical landings would be more difficult than anticipated. The Pogo's delta wing was perfectly suited for pulling into the vertical landing position. It was an advanced design that was already being successfully used on other high-performance aircraft being developed by Convair. The XF-92A experimental test plane was Convair's first attempt to incorporate the delta wing. In this case, the goal was to achieve sustained supersonic flight. Studies had shown that a 60-degree delta was far superior to a swept-wing design from the standpoint of drag, stability, and control. In September 1948, the XF-92A took off from Edwards Air Force Base and broke through the sound barrier. The world's first powered Delta was a success, and Convair would build Delta Wing fighters into the 1960s. But in the Pogo's case, the Delta Wing was selected not for supersonic flight, but for its high resistance to stalling. The transition to vertical hover required a relatively slow airspeed. With a Delta, a stall would be next to impossible. Located 16 miles from San Diego, Brown Field had been selected as the site for the second stage of the Pogo's flight test program. Coleman performed over 70 vertical hover tests in preparation for the first transition to horizontal flight. On November 2nd, 1954, the Convair team was ready. It had been 7 years since the Navy had first contemplated the development of vertical takeoff aircraft. In that time, however, a voice had grown within the Navy that was now suggesting the tail-sitter concept should never have gone past the research stage. Despite the outspoken critics, it was of no concern to Coleman. On this day, his job was to make the Pogo fly, not worry about its future. Coleman believed that the initial transition to horizontal flight would not be difficult. The return to vertical flight, the hovering descent from altitude, and the final descent to an exact spot landing would be infinitely more difficult and dangerous. As usual, the liftoff was flawless. By now, taking off was second nature to Coleman. And the transition, this too was executed masterfully with a smooth application of power and a gentle pushover. There was no more than 50 feet under the ventral fin during the whole graceful maneuver. The muscle-packed engine that had been designed to pull the Pogo straight up would now show what it could do in level flight.
It had a thrust-to-takeoff weight ratio of better than 1, so bingo, you know, to get going, and it had tremendous performance, and it flew well in the air.
The Pogo could fly at nearly 600 miles per hour. It had no drag devices, no speed brakes. Even at flight idle, it was too fast for the AD-5 chase plane. Using all of its 2,500 horsepower engine, the chase plane just could not keep up. The Pogo was both the slowest and the fastest propeller-driven aircraft in history. Proposed armament for the Pogo comprised 4 20mm cannons and wingtip pods, or 48 folding fin rockets. The initial concept called for deploying these tail-sitters on the backs of various ships of the task force. Once a radar threat was known, they would be launched from their ships and guided into the attackers. Like a mobile aerial picket line, the Pogos would then engage the attackers until carrier aircraft could arrive. Indeed, that was the theory behind the VTOL fighter. But theories often look better on paper than they do in real life. Still, the Pogo was showing more promise than its rival. Lockheed's tail-sitter was not performing as well as Convair's Pogo. The XFV had been flying more than the Pogo, but no vertical takeoffs or landings were being attempted. Instead, horizontal and vertical transitions were all done at altitude. The short, stubby, straight wings proved problematic. When transitioning from horizontal to vertical flight, the XFV was unstable. Herman Salmon, the pilot, remarked that in a shallow transition at about 30 degrees, the aircraft would want to roll and become quite unmanageable. The aircraft would stall until finally, at about 80 degrees, when almost vertical, it would be easy to handle again. While it could make the transitions, it had a harder time making them.
The Convair and the Lockheed turboprop-powered VTOL aircraft look different, but in fact they followed exactly the same principles. They had a very powerful turboprop in the nose, with a slender fuselage, wings, in one case a cruciform wing, and they used the controls that were there for normal wing-borne flight in VTOL flight. They flapped the rudders and they flapped the elevators and they flapped the ailerons, all of which were in that very well understood propeller slipstream.
In the end, the Lockheed team decided to put an end to the project. The head flight test engineer himself wrote a letter to the Navy. In it, he simply requested that they terminate the program. After some 20 minutes of conventional flight time, Skeets Coleman was ready for the moment of truth. Flying as low as possible to the ground in idle power, he pulled into a sharp climb. Thanks to the delta wing, there was no stall. At the peak of the climb, Coleman applied power just enough to acquire vertical hover. Going straight up required 3 different configuration changes at the same time. The seat had to be rotated up, the trim adjusted, and power applied. For the descent, Coleman then had to ease the throttle back and redirect his attention from the instrument panel to the ground below. Looking down, back over his shoulder, he had to keep his eyes on the tarmac until touchdown. The entire process was unimaginable to most pilots, and yet Coleman had made it look as smooth and natural as if he'd made a conventional landing. When he repeated the same spectacular demonstration for the Navy and national press 2 days later, the crowd was thoroughly impressed. The world's first vertical takeoff and land aircraft was an exciting accomplishment. The question now was, would the Navy actually use it?
It takes off straight up. It flies level at over 500 miles per hour. The first man in history to fly the Navy's new XFY-1 fighter plane, designed by Convair, is Convair test pilot J.F. Skeets Coleman, a man who smokes for the pure pleasure of smoking.
The U.S. Navy, by 1954, was beginning to reevaluate the VTOL program. The skeptics insisted that what the Navy intended was unrealistic, and the tail-sitter concept terminally flawed. True, they conceded the Pogo was an impressive machine, and yes, it was successful in flight tests. But as a convoy fighter, real-life operation was a different matter.
All these tests took place in clear weather. Nice bright skies, sunshine, and the rest of it. Whereas what the Navy were really after was an aircraft that could operate from a ship in pitch and roll in rough seas and bad visibility. And they never hacked that one. It wasn't an inviting prospect, I should say, as well.
The The arguments for a VTOL combat aircraft varied. The most popular justification for its development was the convoy fighter, where one would be installed on a merchant vessel, poised upward, ready to defend its ship. But others argued that an attack could still slip through undetected. Submarines could still pose a serious threat to merchant shipping. For that matter, the Naval Task Force as a group was considered a vulnerable target. What with the advent of nuclear weapons and supersonic aircraft, the call was for dispersion and mobility. Air power was part of the answer, but airfields can be destroyed again and again. Convair offered a solution, a flying task force that was completely divorced from the airstrip. A water runway is virtually impossible to knock out of action. Convair had built the R-3Y Tradewind as a cargo carrier for the U.S. Navy, but the company proposed a more enhanced role for the huge flying boat, logistic transport. It would form the backbone of an integrated weapons system designed to hold and support advanced base operations. The concept was called the Mobile Base System, and it was comprised of aircraft that could operate free of fixed installations. Here, Convair demonstrates how the enormous hull of the R-3Y could be filled with assault troops, vehicles, and machinery. Like an amphibious invasion, these flying boats would be sent to supplement the carrier strike force by securing an advanced base. Like the Pogo, the R-3Y used the powerful T-40 turboprop. After reaching its destination, the R-3Y could then taxi up to any beachhead and deliver its cargo. The idea was to establish a waterborne support and holding force. But this force would need its own strike capability. Convair had just the aircraft in mind. The XF-2Y Sea Dart. This was an advanced experimental plane that Convair introduced in 1952. Built as a supersonic fighter for the U.S. Navy, it sported the trademark delta wing design. But it was unlike any other fighter built by Convair. Extending two hydroskis beneath its streamlined fuselage, the Sea Dart was able to land on water. It was the world's first and only supersonic seaplane, and it seemed ideally suited for Convair's proposed mobile base concept. It was a forward strike aircraft that needed no fixed runway. Under this mobile base system, the beachhead could be dispersed over many miles of coastline, not concentrated on a heavily defended airstrip location. Costly amphibious landings would be unnecessary, and to protect the advancing troops, the third component of this integrated weapon system, the XF-Y Pogo. It was no seaplane, but it could operate without an airstrip. For tactical close-air ground support, the Pogo was a necessary ingredient to the operation of an effective mobile base system. Clearly, Convair argued, the Pogo showed potential far beyond its convoy fighter role. In theory, it was an intriguing concept, but in actuality, the mobile base system drew little support within the Navy.
Things that they talked about were largely possible. But whether they were the actual best ways to do things or not, I don't know. History hasn't, I don't think, either condemned it or validated it one way or the other.
The R-3Y would join the Navy in 1956 as part of the Naval Air Transport Service. Restricted to hauling cargo across the Pacific Ocean, it was never integrated into a mobile base system. In fact, the flying boat in general was already fading from naval aviation. The Sea Dart remained as an experimental aircraft, but would never join the Navy. By 1957, the test program was canceled. It was undoubtedly a remarkable achievement, but the Navy, in the end, found no use for it. Needing special equipment and tenders, it required more care than it was worth. Needless to say, the mobile base concept never went beyond the proposal stage. Support for continued development of traditional naval aircraft was too strong to continue a costly test program like the Sea Dart. And the Pogo, its future was uncertain at best. It became increasingly more difficult to justify its role in naval operations. But even had a requirement existed, the Pogo still had some unacceptable control problems, despite Coleman's skillful demonstrations. When in the hands of anyone else, the results were nearly disastrous. The backup pilot, John Knable, attempted vertical flight without prior training on the tether rig.
Okay, John, give her a little power.
Here, Skeets Coleman tries to guide him through the hub.
Oh, boy. All right, let's come off the power. Let's come off the power. Take it easy. Down. Bring her down, John. Back at power. Back at power, John. Back at power. Keep her. That's it. You're right straight. Now bring her back at power a little bit. Bring her back at power. A little right aileron. A little right aileron. Bring her back at power, John. Bring her down. Bring her down. Right aileron. Okay, a little left aileron. Right aileron, John. That's it. You got her under good control. But keep her going. Keep her going up. Power, power, John. That's enough. That's enough. Put your nose up. Nose up. Okay, a little right under. Keep her straight now. Easy on the controls, John. Easy on the controls. Bring her down. Bring her down, boy. Bring her down. Come on. A little off in power. Bring her down. Not too much. Atta boy. Okay. Cut. Okay, John. You can hold her a minute. Shut down.
The most unnatural position to fly, and when they'd come to the vertical after doing a decelerating transition, they had effectively to feel for the ground, and no view downwards and behind them at all. That was one of the problems. I mean, the pilot couldn't see behind him and didn't know how far off the ground he was. Very difficult. It wasn't a natural piloting position by any means, and it's not a position that I think pilots would ever get used to. I mean, again, all this flying was done in clear blue skies and the rest of it, of course, and so they never really tested it under adverse meteorological conditions or with a big gusting wind.
In 1956, Convair set up a tether rig at Brown Field to resume pilot training. Skeets Coleman had made his longest and final flight on June 16, 1955. He had already received the prestigious Harmon Trophy for being the first man to successfully take off vertically, transition to horizontal flight, and return for vertical landing. Under his control, the Pogo was indeed a graceful machine. The inevitable happened on August 1st, 1956. The experimental test program of the XFY-1 Pogo stick was officially terminated. By then, despite its accomplishments, the Pogo had lost its support within the Navy.
It worked and worked fine. There wasn't any problem with it. The engines were good, but no requirement. The threat vanished. It didn't exist anymore.
Since the birth of seaplanes, naval aviation has adapted to the changing face of modern warfare. The Pogo was conceived for a specific need, but that need had faded before the aircraft could be perfected. Imagine landing the Pogo on this deck, trying to work its confusing hovering controls while straining your neck, looking backward to see the landing area. It was an unrealistic notion. Even the seagoing helicopter today operates at great risk, and its duty is quite limited. the U.S. Navy would never entertain the tail-sitter concept again.
Over the years, scientists and designers across various nations have devoted efforts towards crafting aircraft with the most minimal takeoff and landing requirements. This approach aimed to reduce the demand for expansive landing sites, thereby enhancing operational versatility. However, achieving such benefits posed significant challenges, prompting aircraft manufacturers to seek unconventional technical solutions. Among the pioneering aircraft to successfully demonstrate shortened takeoff and landing capabilities was the Ryan VZ-3 Vertiplane. In the 1950s, American company Ryan Aeronautical embarked on the development of innovative aviation technologies aimed at improving these crucial flight characteristics. Leveraging a combination of established and novel technical solutions, the company aimed to produce an experimental aircraft meeting the desired specifications. The underlying technologies of this pilot project held promise for potential application in the creation of practical aircraft in the future. First of all, such a technique could interest the Army. To reduce the takeoff distance or to ensure vertical ascent into the air, different methods and designs of the aircraft can be used. In their new project, the designers at Ryan decided to apply the technology of deflecting the airflow. The wing of the aircraft of the new model was to be equipped with developed flaps of a large size that could have a significant impact on the movement of air, changing its direction and creating additional thrust. To test the original proposal in practice needed the help of a specialized experimental aircraft. The new project was assigned the working corporate designation Ryan Model 92. Following the expressed interest of the US Army in its development, a new designation emerged, VZ-3, along with the fitting name Vertiplane. Over time, the military designation of the project was further supplemented with new letters, VZ-3RY, under which it gained widespread recognition. The objective of the VT-plane project was to construct an experimental aircraft capable of vertical or shortened takeoff and landing. It aimed to practically test original concepts that could significantly simplify the design. The experimental aircraft wasn't intended for payload carriage or weaponization, hence eliminating the necessity for high load capacity or specialized equipment. Only elements directly pertinent to the project's primary objectives were to exhibit comparative complexity. The proposed design for the VZ-3 aircraft entailed a high wing configuration with two propellers mounted on underwing gondolas and a fixed landing gear. Its fuselage featured a large teardrop-shaped elongation. Notably, the nose and central sections of the fuselage, distinguished by an enlarged cross-section, boasted vertical sides and a horizontal bottom, seamlessly integrated with other surface areas. Additionally, the tail boom sported a tapering truncated cone shape. In the central part of the fuselage, flush with its upper surface, the wing of the original structure was attached. On the tail, it was planned to install a T-shaped tail unit with a small keel sweep and a rectangular stabilizer. The nose of the fuselage accommodated the cockpit for a single pilot. In the first version of the project, the pilot was to enter through a large opening between the roof and the sides of the fuselage. Even in the initial stages of the project, it became apparent that the cabin glazing design would not offer the necessary visibility during takeoff and landing. Consequently, an additional window with glazing was incorporated into the bottom of the nose fairing, enabling the pilot to maintain visual contact with the runway. The primary innovation of the Ryan VZ-3 project lay in its unconventional wing design, featuring elaborate mechanization directly influencing the aircraft's key characteristics. The proposal involved installing a rectangular-shaped high-placed wing in the central part of the fuselage. Despite its relatively modest elongation, other design features compensated effectively for this limitation. Notably, the wing boasted a substantial profile thickness. Two small-sized gondolas housing gearboxes and propeller shafts were positioned beneath the wing. These gondolas featured large trapezoid-shaped combs aimed at mitigating airflow overflow and preventing it from exceeding prescribed limits. The experimental aircraft's wing featured sizable retractable flaps, comparable in area to the wing itself. To enhance takeoff and landing performance, these flaps could extend from the wing and tilt backwards, assuming a position close to vertical. Additionally, the wing, flaps and tip ridges formed a box-shaped system designed to significantly influence aerodynamics and effectively redistribute airflow. It was due to the redistribution of the flow and the direction of the air downwards that we're supposed to get a shortened or even vertical takeoff. The experimental aircraft received an unusual power plant equipped with 2 propellers. The Avco Lycoming T-53L1 turboshaft helicopter engine with a power output of 1,000 horsepower was situated in the rear fuselage. Air intake was facilitated through a bottom-mounted intake device and an internal channel of minimal length, while fuel was sourced from built-in tanks. A shaft positioned in front of the engine transmitted power to the central gearbox, which in turn distributed torque to 2 shafts running parallel to the wing spars. Subsequently, power was transferred to the propellers through a series of gears. 3 bladed propellers were affixed to the shafts emerging from the underwing gondolas, allowing for the gondolas to maintain a minimal size. Their width remained consistent with the pylons on which they were mounted, thereby minimizing obstruction of the plane's surface area. Each propeller boasted a diameter of 2.79 meters, effectively covering nearly the entire frontal projection area of the wing, thereby positively influencing flight performance. The experimental aircraft of this new model was designed to exhibit acceptable controllability across all flight modes. To achieve this, it was equipped with both traditional control surfaces and non-standard mechanisms serving similar purposes. Pitch and yaw control during speed flight modes were intended to be managed by the elevator and rudder respectively, situated on the stabilizer and keel. At low speeds, such devices sharply lost their efficiency, which, in addition to them, there was developed a system of gas rudders connected to the engine. The plane couldn't be completed with ailerons for this reason. The roll control was proposed to be carried out by changing the operating parameters of the 2 propellers. An increase in the thrust of one of the screws caused the corresponding plane to rise upwards under the action of the increased lift force and thus led to a change in roll. The initial version of the Ryan VZ3 Vertiplane project featured a 3-point chassis with a tailwheel. The primary supports of this chassis comprised 3 tubes of varying lengths with wheels situated beneath the central fuselage section. A tail skid was positioned at the rear. Due to the aircraft's aim for minimal takeoff weight, provisions for retracting the chassis were not included. The dimensions of the first version of the aircraft were as follows: length 8.3 meters, wingspan 7.14 meters, height 3.25 meters. The normal takeoff weight was set at 1,180 kilograms, with the aircraft designed to be operated by a single pilot located in the forward cabin. The restricted takeoff weight constrained fuel capacity, with high speed and extended range not being primary project objectives. Instead, the focus was on achieving favorable takeoff and landing characteristics. The pilot project was completed in 1957, and by early the following year, the first prototype underwent testing. On February the 7th, it was transported to the airport for ground tests, which preceded its inaugural flight. Prior to this flight, extensive ground testing and wind tunnel trials were conducted over the course of nearly a year. The efforts yielded valuable insights into the aircraft's behavior across various modes of operation and identified areas for necessary improvements. According to the results of ground tests, an experienced aircraft was allowed to fly. The first flight of the experienced Vertiplane took place on January 21, 1959. The use of large flaps, together with the wing forming a box-like structure, gave certain results. In practice, it revealed the possibility of a sharp reduction in takeoff and run. At the same time, it wasn't without its problems. The initial challenges with the 1,000 horsepower engine became apparent early on, as it failed to generate the necessary thrust to take off without a sufficient headwind, resulting in extended run-up requirements. Furthermore, occasional handling issues arose under certain conditions. The primary focus of the test flights was to ascertain the actual performance characteristics during takeoff and landing modes. Evaluation of the aircraft's behavior in horizontal flight was of secondary importance. Testing revealed that the current configuration still couldn't execute vertical takeoff. Nevertheless, it showed promising potential for reducing run-up and runway requirements, albeit often reliant on favourable headwinds. Throughout the first months of 1959, Ryan Aeronautical and US Army specialists managed only about 24 relatively successful test flights. Unfortunately, during the 21st flight, the experimental VZ-3 experienced a mishap resulting in damage. Despite this setback, the decision was made to restore the aircraft and continue testing. However, shortly after the accident and the commencement of repairs, the US military lost interest in the unconventional project and withdrew its participation. This decision was influenced by various factors, leading to a halt in further collaboration on the project. However, the aircraft was still needed by science, because of which, after repair, the prototype was transferred to NASA. Further work was carried out by the Aerospace Agency specialists. The tests were resumed in February 1960, but soon stopped again. During the next descent into the air, there were problems that forced the pilot to leave the car. Fortunately, the aircraft sustained minimal damage and was deemed repairable. This presented an opportunity to implement several new solutions inspired by the breakdowns and subsequent repairs. The prototype wasn't merely restored, it was also reimagined according to an updated project plan. These enhancements were informed by ground and aerodynamic tests, as well as insights gained from the initial test flights. Foremost among the changes was a significant overhaul of the chassis. The design of the main landing gear underwent modifications, and the tail skid was replaced with a fixed nose strut. This adjustment altered the aircraft's stance on the ground and during takeoff runs, requiring it to rest level with a slight nose-down attitude. Refinements to the chassis, aimed at enhancing visibility during takeoff and landing, prompted the removal of glazing from the nose fairing. Furthermore, the cabin underwent a transformation, shedding its existing glazing and roof. Now, only a small visor remained to shield the pilot, with no additional elements of the canopy present. Additionally, a portion of the metal fuselage skin in the nose section was replaced with linen material. Measures were taken to change the aerodynamics of the aircraft. In place of the crutch under the fuselage, an additional comb appeared, which improved the stability along the course. To improve the characteristics of the wing, deviated slats appeared on the plane. Also changed were the size of the flaps. Various modifications were implemented to simplify or enhance specific elements of the aircraft and improve its aerodynamic performance. By the end of 1960, NASA experts once again brought the experienced Ryan Vertiplane to the runway. Inspections of the aircraft continued until 1961, primarily focusing on studying its takeoff and landing characteristics with different wing configurations, controllability in various modes, and other factors. Horizontal flight characteristics were also evaluated multiple times throughout the testing process. Over several stages of testing, interspersed with repairs, a wealth of diverse information was gathered. The prototype VZ-3 was subjected to testing at speeds ranging from 6 knots, 11.1 km an hour, to 80 knots, 148.1 km an hour, and demonstrated acceptable performance across this spectrum. Optimal takeoff and landing parameters were achieved within the 20 to 25 knot range, 37 to 46 km an hour. For instance, at speeds of approximately 35 km an hour, the aircraft required 9 to 10 meters of runway, slightly more than its own length, to take off. Maintaining lift at this speed allowed the aircraft to ascend to an altitude of 1.1 kilometers. Early in the testing phase, pilots encountered the phenomenon known as ground effect. At altitudes below 5 meters, air currents reflecting off the ground began to adversely affect the operation of the propellers and wing, reducing their efficiency. Additionally, aircraft stability diminished, potentially resulting in an uncontrolled dive and subsequent crash. Incorrect use of gas rudders exacerbated these risks during such conditions. The negative impact of the underlying surface particularly hampered the implementation of the landing. Nevertheless, recommendations were soon formed on the optimal modes of descent and touching the ground. To avoid loss of control and fall, the pilot on landing, dropping below 15 feet 5 meters, had to withstand speeds of around 20 knots. Maintaining a descent angle of several degrees was crucial during landing. Experimental trials pushed the landing speed to 40 knots, 74 kilometers an hour, and the descent angle to 16 degrees, but such landing modes pose significant risks. From the initial wind tunnel tests, it was evident that the Ryan VZ-3 Vertiplane, despite its name, would not be capable of vertical takeoff and landing, a conclusion confirmed during full flight tests. Nevertheless, the project's creators achieved a substantial reduction in runway length, aligning with the original project objectives. Testing of the prototype, revamped according to the updated project specifications, persisted until 1961. Following their conclusion, American experts meticulously analyzed the amassed data, producing numerous reports and scientific works. This comprehensive study spanned several years, shedding light on various aspects of the aircraft's performance. By this time, the prototype had been relegated to storage, with little hope of resuming flights. Indeed, after 1961, the experienced VZ-3 never took to the skies again. After all of the required research and scientific work was completed, the car was decommissioned as superfluous. Unlike some other unique examples of aviation technology, the only VT plane was not dismantled for metal. The aircraft was handed over to the Army Aviation Museum, Fort Rucker, Alabama, where it remains to this day. It's worth noting that the prototype Ryan Model 92 VZ-3 Vertiplane wasn't the sole platform dedicated to testing and refining innovative concepts aimed at enhancing aircraft takeoff and landing capabilities. Throughout the 1950s, numerous similar-purpose aircraft were developed and tested by several other US aircraft manufacturers. Like the VZ-3, these aircraft merit separate examination and review for their contributions to advancing aviation technology in this regard.
Even today, a scene like this seems almost unbelievable. A man floating in space while way below the world spins past. The trail of technology that allows us to experience such an amazing feat has its roots deeply embedded in the X-Plane series. By the end of the 50s, spaceflight was becoming a reality, and the Boeing X-20 concept seemed like the direction it was all heading. Powerful multi-stage rockets would boost the X-20 into orbit. Re-entry and landing would be by unpowered glide. During World War II, German researchers proposed a bomber using this boost glide system. It would skip across the upper atmosphere at 13,000 miles per hour. The X-20's proposed use of this dynamic soaring gave it a foreboding name: the Dinosaur. In 1961, research was well underway. Thermal experiments were essential. The Dinosaur would need to withstand incredible extremes of heat and cold. Technology was at its limits as researchers simulated speeds nearing 17,000 miles per hour. Although scheduled for flight in 1965, the Dinosaur, like its namesake, was headed for extinction. A program that promised a pilotable, reusable spacecraft almost 20 years before the shuttle was canceled in 1963. The U.S. was taking the most expedient way to reach space. Expendable rockets and space capsules were a faster answer to the Soviets' early space race lead. The X-20's slower development and high cost couldn't compete with the quick and easy capsule method. As the space race drew closer to putting a man on the moon, researchers still worked at perfecting shapes that could conceivably fly to space and back. Launched from a helicopter, the Hyper 3 was a half-scale glider, built to test ideas a generation beyond the ill-fated Dinosaur. It was piloted remotely from a ground-based simulated cockpit. The Hyper 3's specially shaped body provided all its lift. Small, straight, retractable winglets allowed lower-speed landings. This lifting body configuration was projected as the shape of the space plane of the future. In the late 60s, the Martin Marietta X-24A, along with other lifting body aircraft, helped develop many aspects of flight without wings, including safe, steep approach landing methods crucial to the success of this kind of aircraft. In June 1971, the X-24A was retired, but researchers were still eager to investigate other configurations. As the glamorous Apollo missions drained cash flow, budgets were tight, so plans were drawn up to glove the existing airframe with a dramatically different shape. Jerry Gentry flew the X-24A for the Air Force.
In essence, they just changed the bottom of it from essentially an oval shape and made it into a very slender delta. And so they were able, at minimal expense, to look at two different configurations rather inexpensively.
The idea was to retain the existing and already proven systems of the old aircraft and fit a brand new body around it. The Flying Potato would be transformed into a sleek Flying Dagger. The new shape was a blended body and wing, aesthetically far removed from its previous form. Stunningly transformed, the new X-24B rolled out of Martin Marietta's Denver facility on October 11, 1972, 10 months after the A-model shell was delivered. Extensively modified, it had grown 15 feet longer. Its flat iron shape, exhaustively tested in wind tunnels, promised excellent handling qualities. It certainly looked like the shape of the future. The X-24B was designed to be air-launched. Modified B-52 bombers used for the X-15 were pressed into service. As a cost-cutting measure, the X-15 mounting pylon was modified with an adapter for the X-24. NASA test pilot John Mankey had flown the X-24A. On November 15, 1973, he would become the first to fly the new configuration under power. His observations would prove invaluable in comparing the two shapes' performance and handling qualities. The rocket power plant was the same trusty XLR-11 type that had pushed the X-1 through the sound barrier 26 years before. The handling qualities of the X-24B were very much to the pilot's liking. The double delta shape gave 2 times the lift and 3 times the maneuverability of the old configuration. The feel was more like a fighter, more responsive and flyable than the pure lifting body of the X-24A. The X-24B's most striking feature, its long pointed nose, was designed for a very good reason. It was found that the rounded stubby nose of the earlier form, although desirable to combat re-entry heating, was a handicap at lower speeds. With its sharp triangular form, the B model allowed much better handling and stability during its steep landing approach. By August 1975, the Space Shuttle project was well underway, drawing many ideas from the X-24B. The huge flat dry lake runways at Edwards were invaluable, but the shuttle needed verification that the proposed steep power-off landing method could be accomplished on a conventional runway. The X-24B showed that it could make accurate and safe landings on concrete. NASA pilot Bill Dana flew most of the lifting bodies and was a veteran of the pioneering X-15 project that had taken man higher and faster than any winged aircraft. He found the X-24B different in many ways, but familiar in others.
It was a very benign flight compared to an X-15 flight, but the approach and landing were identical in the two airplanes. A steep power-off landing with the landing gear coming down very late in the flight. And in that aspect, why the X-24 was very similar to the X-15.
Dana's first X-24B flight had taken place early in September 1975. The little craft had easily pushed up to Mach 1.5 and reached 71,000 feet. By that time, the 24B had already proved itself a much greater performer than the X-24A. In May 1975, John Mankey had taken the X-24B to its highest altitude of 74,130 feet. The previous year, U.S. Air Force pilot Colonel Michael Love had clocked a speed of Mach 1.76, or 1,163 miles per hour. Bill Dana's second flight was the X-24B's final powered flight. As the XLR-11 rocket engine shut down, Dana had just pushed the little bird into supersonic flight. At a conservative altitude of around 57,000 feet, he prepared for the fast glide down with the familiar steep landing approach. This method of landing had proved very efficient and accurate. The pilot almost had only to point the aircraft at the spot where he wanted to touch down on. When activated, the X-24B's rugged landing gear snapped out amazingly fast. The pilot would wait for the last possible moment to drop the gear, as the drag caused loss of precious speed, lift, and control. Power-off landings left no second chances.
I think the major contribution of the lifting bodies to technology to date has been the demonstration that a variety of various shapes could be landed power off, even though they had steep final approach glides.
The X-24B's final powered flight in September 1975 also marked the final rocket flight of the X-plane series. Ironically, it operated with the same type of engine used on the first X-plane. The Martin Marietta X-24B is now on display at the United States Air Force Museum in Dayton, Ohio. The most advanced of the lifting bodies retired, as the space shuttle was being readied for its debut. The evolutionary trail towards the shuttle was completed by this truly unique aircraft.
The original space shuttle intended to carry 4 or 5 jet engines and extend them after re-entry, light them up, and then make a power-on landing. And through our experiences with the lifting bodies and our ability to successfully land power-off a number of different shapes, we convinced NASA Houston to remove the landing engines and the jet fuel from the space shuttle. This reduced the orbital weight of the shuttle 35,000 pounds and reduced the launch weight by 1 million pounds.
The orbiting shuttle is in some way the realization of the X-20 dinosaur. Boosted into orbit like the Apollo capsules by jettisoned rockets, the shuttle is a pilotable, reusable system. Thanks to the invaluable data provided by the lifting bodies, it can make a controlled, gliding re-entry and descend to a safe pinpoint landing anywhere on Earth. However, the lifting bodies may still have a lot to offer the next step, beyond the shuttle. The future of the X-planes looks exhilarating. These computer images are of the shockwave pattern around the X-30, the proposed NASP or National Aerospace plane. Designers use supercomputers to provide data that wind tunnels can't give us. This part airplane, part spaceship will need to fly over 17,000 miles per hour and survive the tremendous heat loads of accelerating into orbit and re-entry. New materials with greater heat resistance, lighter weight, and greater strength will also need to survive the extremes of ultra-cold. New alloys and carbon fabrication technologies will be stretched to the limits. With all this information from simulation and supercomputers, we know pretty much what to expect, so why should we build the X-30? Scott Crossfield, X-plane test pilot and aerodynamicist.
If you could do things with unmanned systems, with computers, you might just calculate what you want to do and then not bother to build the system. This is a human experience, this thing of being on Earth. The Russians saw the backside of the moon first, but we had a man on there first. And the strides that we took in the technology understanding the moon are orders of magnitude more than they learned just by flying around the backside of it, huh? Or with the unmanned systems that land on the moon.
NASA and the Department of Defense have been exploring hypersonic technologies for years. Each X-plane can almost be seen as a building block of knowledge working towards the X-30. The National Aerospace plane will be a single stage-to-orbit space vehicle, able to take off under its own power and fly into orbit around the Earth. After completing its space mission, the X-30, like the shuttle, will make a long, unpowered, gliding descent, re-enter the atmosphere, and land on a conventional runway. Jay Miller, aviation historian.
In fact, the NASP is point A. It is a research tool. It is an exploratory tool. It is hardware that will allow us to prove whether or not we can build a vehicle that will basically be single stage to orbit.
The X-30's flight tests will be in carefully monitored increments, adding speed a little at a time. Computers will use this data to stay ahead of the game, searching for hot spots on the X-30's skin that, if not discovered, could eat up the plane during hypersonic flight. Many of the lessons learned from the X-15 and lifting body programs about aerodynamic heating, shockwave patterns, and countless other subjects form the huge database that researchers refer to. The National Aerospace Plane Project stands on the shoulders of its pioneering X-plane predecessors. After many years, they continue to yield priceless information, even of a more down-to-earth nature.
There's no question that the National Aerospace Plane will use techniques developed to land the X-15 and to land the lifting bodies when they're learning how to set up their approach pattern for the X-30.
Originally conceived as a Concorde-like sleek space shuttle, now as the X-30 takes shape, it seems to be a much more radical design. Maybe the lifting body has found its time. Jerry Gentry, lifting body test pilot.
The lifting body program, people lost obvious interest in that when the decision was made on the space shuttle configuration. A great many people thought at one time or another that the lifting body would probably be the configuration for the space shuttle. What's interesting is to see now what the configuration is for the National Aerospace Plane, or X-30, and indeed it is a lifting body again. So the lifting body is starting to return to vogue or popularity.
The affirmation of the lifting body shows how so much high-technology research is a matter of planting the seed of an idea and many years later seeing it bear fruit. Such a huge project could never be attempted by one company. The National Aerospace Plane will involve 5 major aerospace companies in a huge consortium effort controlled by NASA and the Department of Defense.
The difficulty lies that when you're trying to build a single stage to orbit vehicle, you're looking at a very expensive platform, particularly when you're talking about a limited production vehicle. I mean, they're not going to build but maybe 2 or 3 of these aircraft. And they are strictly research vehicles to prove certain points, to achieve certain performance objectives.
But the scramjet power plant has yet to be invented. Just to start one up would be like lighting a match in a hurricane.
The scramjet is kind of the next generation, if you will, of propulsion systems. It is kind of the ultimate jet engine.
Like all X-planes, the X-30 will tackle seemingly insurmountable problems and open new doors. Scott Crossfield, involved with X-planes from the X-1 to the X-15 and now the X-30, is still a great believer in the research airplane.
I'm determined we're going to catch up with where we left off on the X-15 with the National Aerospace Plane. The limitations being largely economic. It's not technical. We know more about the National Aerospace Plane today than we did at the Apollo, the X-15, the Mercury at this stage. So that's my thesis. And it's a natural extension of what's proven successful, the research airplane program.
The promise of the X-30 National Aerospace Plane is viewed as the ultimate X-plane. The payoff will be just like the other projects, new ways of flying, building, and powering the next generation of flying machines. The dreams that were stirred in the heady days after World War II as the X-1 flew into supersonic flight for the first time are still alive. But there can be no ultimate X-plane, as there will always be another goal to reach, another door to open, and another X-plane to fly into the unknown.
Throughout the 1950s, major aircraft manufacturers in the United States were eagerly exploring the potential of vertical takeoff and landing (VTOL) technology across various military applications. With the looming threat of intercontinental ballistic missiles and thermonuclear weapons, the military sought VTOL aircraft capable of operating from small dispersed sites without relying on traditional air bases or aircraft carriers, targets that were increasingly vulnerable to attack. A key concept driving this pursuit was the notion that an aircraft with a thrust-to-weight ratio exceeding 1 could vertically launch, transition to horizontal flight for mission execution, and then return for a vertical landing. Such capabilities promised to eliminate the need for expensive and easily targeted runways, enhancing the aircraft's survivability and operational flexibility in a rapidly evolving strategic landscape. Among the pioneers in this endeavour was the Ryan Aircraft Corporation, which endeavoured to translate this concept into a practical fighter aircraft for the Air Force with its X-13 Vertijet. However, like most other VTOL aircraft, the performance compromises made for their unique capabilities did not warrant its introduction in place of more capable conventional aircraft. The idea for the Vertijet originated just after World War II, when engineers for Ryan casually debated whether or not their FR-1 Fireball, which had a thrust-to-weight ratio of 1 at low fuel quantities, could take off vertically. The vertical takeoff idea soon advanced beyond the discussion stage. In 1947, the Navy's Bureau of Aeronautics enlisted Ryan for a contract aimed at exploring the technical complexities associated with developing a vertically launched jet fighter, a pivotal aspect of a broader initiative to assess the viability of submarine-based aircraft. Concurrently, the Navy funded a series of experimental tail-sitter aircraft comprising conventionally configured planes outfitted with large counter-rotating propellers designed to rest vertically on reinforced tail sections. Notable examples included the Convair XF-Y1 and Lockheed XF-V1, intended to utilize their high-thrust propellers for vertical takeoff from various naval vessels, thereby furnishing defensive air cover without the need for aircraft carriers. Ryan's engineering analyses demonstrated the feasibility of a comparable jet-powered design, augmented by a reaction control system capable of redirecting exhaust gases to facilitate control during hovering and low-speed flight. Subsequently, a Navy contract facilitated the construction of an unmanned flying prototype, which conducted its inaugural flight on October 20th, 1950. This peculiar contraption, affectionately dubbed the Beast in the Backyard, was propelled by an Allison J-33 turbine and employed a ball-mounted nozzle to provide reaction control while hovering. Ryan engineers converted a B-47 fuel tank into a cockpit to allow test pilot Peter Girard to evaluate the testbed's suitability as a manned research aircraft, which sat on its tail to take off vertically. On November 24, 1953, Girard made the first manned hovering flight in a jet aircraft with this unusual machine. After Navy funding ran out, the Air Force became interested in Ryan's experiments and in July 1954 issued a contract to the company to construct 2 VTOL tail-sitter demonstrators designated as the X-13 Vertijet. This project, based on the earlier Navy design proposal, was to demonstrate the suitability of easily dispersible VTOL fighters. Under the guidance of Chief Engineer Curtis Bates, the X-13 emerged as a compact, single-engined delta-wing fighter, with its distinctive features being a set of winglets and fixed landing gear, elements that might appear ordinary to the casual observer. Spearheaded by Robert Furman and the Ryan Technical Section, the aircraft was meticulously designed to be transported on a specialized trailer, capable of tilting vertically to facilitate the launch and recovery of the X-13 during vertical takeoffs and landings. In late 1955, Ryan successfully completed the first Vertijet, serial number 541619, and on December 10th, Girard piloted its maiden flight. Initially equipped with a fixed tricycle landing gear, the X-13 underwent testing as a conventional aircraft. Furman and his team prioritized exploring the conventional handling characteristics before risking vertical flight testing. Following the resolution of oscillation issues through the installation of dampers, engineers affixed a temporary steel tube truss with custering wheels to the rear of the X-13. This modification allowed the aircraft to assume a tail-sitting position during vertical flight testing, eliminating the need for the complex launch and recovery procedures associated with the launch trailer. Pete Girard made the first vertical takeoff and landing on May 28, 1956. On the same day, the second X-13 made its first flight. The aircraft was agile and responsive in conventional flight. As the aircraft transitioned to a nose-high attitude to achieve a hover using the thrust from its own engine, a vectorable exhaust nozzle linked to the controls provided a straightforward and efficient means of control. To facilitate the delicate landing process, small bleed air thrusters positioned on the wingtips enabled minor adjustments to the pitch and yaw of the aircraft when necessary. Integrating both conventional and VTOL control systems, a stability augmentation system ensured smooth transitions without requiring abrupt changes to pilot control inputs. During vertical takeoff, the launch procedure involved raising the bed of the launch trailer vertically. This allowed the X-13 to hang from a cable suspended by 2 arms on the top of the trailer, featuring a partially retractable hook. For vertical operations, flat bumpers replaced each of the main wheels on the fixed landing gear, preventing damage to the fuselage underside if it swung into the trailer bed, thereby facilitating transportation. Subsequently, the pilot would increase throttle until the hook lifted off the launch cable, then maneuver away from the trailer and accelerate vertically, smoothly transitioning to conventional flight. However, vertical landings posed greater challenges and were perhaps the most impractical aspect of the Vertijet concept. Its primary drawback, akin to earlier tail-sitters, lay in the obstruction of the pilot's vision by the airframe, making it exceedingly difficult to accurately gauge the distance to the ground without external assistance. Although the pilot's seat pivoted 45 degrees towards vertical during landing, the pilot still had to approach the recovery trailer blind, with the underside of the fuselage facing the surface of the trailer. Constant radio communication with a ground observer was essential to talk the X-13 into position during the cumbersome process. A 6-meter, 20-foot long folding pole with marked gradations attached to the top of the recovery trailer gave the pilot a clear indication of the distance remaining before he contacted the trailer. Once in position, the pilot gradually reduced the throttle until the nose hook caught the recovery cable. On May 28, 1956, the X-13 executed its inaugural vertical hovering flight, initiating a series of summer tests where Girard and fellow test pilot Lou Everett practiced cable catching techniques using a 1-inch thick rope strung between two towers. To safeguard against potential damage during docking maneuvers with the trailer, Ryan engineers equipped the X-13 with a replaceable wooden nose. On November 28th, Girard accomplished the first ever transition from horizontal to vertical flight and vice versa in the X-13. Then, on April 11th, 1957, he launched from the trailer, seamlessly transitioning to conventional flight, and executed a vertical landing, successfully fulfilling the X-13's mission profile. Illustrating the concept of dispersed operating sites, the second X-13 captivated over 3,000 military officers and journalists with an impressive display at the Pentagon on July 30th, 1957. However, competing programs diverted funds away from the project, leading to the X-13's final flight on September 30th, 1957. Despite later programs like the XV-6 Kestrel and the Aviate Harrier achieving operational success, the X-13 provided an effective solution to the challenges of developing a VTOL fighter within the technological constraints of its era. The Vertijet successfully completed all designated tasks and undoubtedly excelled as an experimental demonstration aircraft, despite the inherent impracticality of the operational concept. Ironically, by the close of the 20th century, the thrust vectoring system, originally pioneered on the X-13, would evolve into an indispensable component of advanced combat aircraft. In 1960, Ryan generously donated the first X-13 along with its launch trailer to the Smithsonian Institution. Conceived during the latter part of World War II, the Miles M57 Aerovan aimed to serve as an economical aircraft for transporting passengers and cargo over short distances, capable of landing and taking off from rugged airstrips. Development of the Aerovan began in early 1944, with the vision of creating a cost-effective, low-powered freighter suitable for both civilian and military applications. George Miles, throughout the Second World War, championed the adoption of such an aircraft in the British military, challenging the prevailing reliance on gliders. After completing the development of the Miles Messenger, Miles's design team recognized the potential of a more powerful and heavier aircraft, approximately double in capacity. This envisioned aircraft could serve as a robust military transport, particularly for operations like the Burma campaign against Imperial Japan and specialized roles such as air ambulance missions. Anticipating post-war demand from civilian operators, Miles foresaw the Aerovan's popularity in the civilian market. However, the War Ministry held a different perspective, delaying the project until the conclusion of hostilities and the Victory in Europe Day celebrations on May 8, 1945. The prototype aircraft was built at the Miles factory in Berkshire, debuting on January 26, 1945. The plane featured a high wing design, a high tail, and large rear clamshell doors. Miles decided that a pair of Blackburn Cirrus major piston engines would power the British-built plane. After its maiden flight, test pilot Tommy Rose gave it rave reviews for its performance. The aircraft was also capable of lifting heavy payloads, something Miles thought the Air Ministry would like. Constructed from plastic-bonded plywood with elements of spruce and metal, the Miles Aerovan was a twin-engined high-wing monoplane. Its design featured a fixed tricycle undercarriage and 3 vertical tail and rudder units, resembling the Miles Messenger in its overall configuration. The wing boasted electrically actuated flaps, a recent innovation allowing adjustment to any angle. Ground steering options included both differential braking and differential operation of the throttles. The Aerovan's forward fuselage had a relatively deep-sided structure, requiring a substantial fin area. The cockpit, situated beneath a large clear perspex canopy, accommodated 2 pilots, while circular windows on either side of the pod-shaped fuselage provided views for passengers. Access to the cabin and cockpit was granted through a starboard side door, with additional amenities like soundproofing often included for enhanced comfort. Known for its lifting prowess, the Aerovan could carry payloads of up to 1 ton, with enough space to accommodate a typical family car, loaded through rear-set clamshell doors. The standard Aerovan was powered by a pair of Blackburn Cirrus major piston engines. Alternative power plants included the de Havilland Gypsy Major and the Lycoming 0435, often necessitating the use of enlarged fins and rudders to cope with the increased power under all circumstances. By swapping the engines, the maximum speed could be increased by up to 20 miles per hour and the rate of climb by up to 50%. Work on the Aerovan was resumed shortly after Victory in Europe Day. While there was immediate demand for the type amongst civilian customers, Miles were not able to keep up with the rate of orders incoming, an outcome which aviation author Don Brown attributed to the Air Ministry's decision to place the project on hold. Diverging from the prototype, the production model of the Aerovan underwent notable changes, including an 18-inch elongation of the fuselage and the adoption of porthole windows in place of rectangular ones. In 1946, full-scale production of the Aerovan commenced, with the majority sold to civilian operators globally. While predominantly a civilian aircraft, some military interest emerged, with Israel and New Zealand among the notable customers. Despite having a license for Aerovan production in France, no such aircraft were ever manufactured in the country. In New Zealand, a single Royal New Zealand Air Force aircraft was adapted for aerial fertilizer spreading, and another for aeromagnetic survey work, though the latter proved unsuccessful. In 1957, a Mark IV model underwent research, with the Hurrell Du Bois high aspect ratio wing becoming known as the Miles HDM 105. Production abruptly halted in late 1947 due to Miles's bankruptcy and subsequent dissolution. The Ryan XV-5 Vertifan was an experimental jet-powered VTOL vertical short takeoff and landing aircraft developed in the 1960s. The United States Army commissioned the Ryan VZ-11RY in 1961, later redesignated as the XV-5A in 1962. This initiative was part of the Army's exploration of VTOL capabilities, alongside the Lockheed VZ-10 Hummingbird, which was later redesignated as the XV-4 in 1962. The XV-5 was equipped with 2 General Electric J85 GE5 turbojets, each providing 2,658 pounds of thrust. Vertical takeoff and landing VTOL capabilities were achieved through the use of General Electric X3535 lift fans integrated into the wings and a smaller fan in the nose. These lift fans were powered by engine exhaust gas. Each wing featured a 62.5-inch diameter lift fan with a hinged cover on the upper wing surface, which could be opened for VTOL operations. The 36-inch nose fan played a role in pitch control but posed challenges in terms of handling characteristics. The lift fans collectively generated vertical lift of approximately 16,000 pounds, which was nearly 3 times the thrust produced by the turbojets. Yaw control was facilitated by a set of louvered vanes beneath each wing fan, enabling the vectoring of thrust fore and aft. The XV-5 Vertifan was a part of the Army's exploration of innovative VTOL technologies during the 1960s, showcasing unique lift fan configurations for vertical takeoff and landing. The engine power setting determined the lift from the fans, as fan RPM was determined by the exhaust output from the J85 engines and the load on the fan. Roll control was by differential actuation of the wing fan exit louvers. Aircraft performance was subsonic, with delta wings superficially similar to those on the Douglas A4 Skyhawk. The Vertifan had an unusual intake position above the 2-seat side-by-side seating cockpit and a T-tail. The XV-5A was painted in army green, while the XV-5B had a white NASA color scheme. Despite its unique design, the lift fans on the XV-5 didn't generate the anticipated thrust, and the transition between vertical and horizontal flight proved to be challenging and abrupt. This aircraft marked one of the last crewed endeavours by Ryan, a company that shifted its focus to drone manufacturing in the mid-1960s. The XV-5 was part of a diverse array of attempts to create successful vertical takeoff aircraft. However, the lift fan system used in the XV-5 was heavy and occupied a considerable internal volume. Only the Hawker Siddeley Harrier remained operational by the turn of the 21st century, along with technology enabling the use of a shaft-driven fan in the Lockheed Martin F-35B. The combination of the J-85 engine and lift fan in the XV-5 was a precursor to developments that led to the first high bypass ratio engine by General Electric, the TF-39. The lift fans were driven by turbine blades mounted around the fan's periphery, with a mass flow 13 times greater than that of the gas generator and resulting in a threefold increase in thrust compared to a propelling nozzle. Following the demonstration that large volumes of air could be moved through a lift fan, an 80-inch tip drive fan, turned through 90 degrees and powered by a more potent J79 engine, was constructed to showcase an efficient cruise fan. This concept of a large diameter cruise fan was incorporated into the General Electric TF-39 engine utilized on the Lockheed CF-5 Galaxy. The XV-5, while not achieving widespread success, played a role in advancing lift fan technology and contributing to subsequent developments in aircraft propulsion. Two 12,500-pound XV-5As were evaluated in late 1966 by 15 test pilots. One was destroyed in a crash during a public flight demonstration on the 27th of April 1965, killing Ryan test pilot Lou Everett. As a result of this accident, the conversion switch was changed to a lift-lock toggle and relocated on the main instrument panel ahead of the collective lever control. The XV-5 presented challenges during landing due to various factors. Yaw control relied on altering the angle of the lift fans in opposing directions, but this method proved insufficient for precise low-speed handling. The duct doors further complicated control, causing significant pitch changes even at low speeds. Additionally, the aircraft experienced poor acceleration during standard runway takeoffs. Promotional materials and tests explored the potential of a rescue version equipped with a winch to hoist individuals into a compartment behind the pilots. However, a tragic incident occurred on October 5, 1966, during trials for the rescue aircraft. The second XV-5 sustained extensive damage when a suspended horse collar survivor sling was drawn into a wing fan. Despite the fan still functioning well enough for controlled flight, Major David H. Tittle, the pilot, suffered fatal injuries due to the ejection seat propelling him out of the aircraft after it hit the concrete airport surface. Following the accident, the second aircraft was reconstructed as the modified XV-5B and testing continued until 1971. An XV-5B is currently on display at the United States Army Aviation Museum in Fort Novosel, Alabama. Despite the cancellation of the program, the ducted fan concept was deemed successful, leading to several proposed follow-up programs. The ducted fans were recognized for their quiet operation, especially for the era, and their ability to operate from standard surface materials without causing damage. This set them apart from other VTOL aircraft, which often require protective mats to prevent ground surface damage from their exhaust, a concern mitigated by the cooler exhaust from ducted fans. Throughout the history of military transport aviation, developers of new projects have consistently aimed to enhance aircraft and helicopter capabilities, including increasing carrying capacity, speed, and range of flight. However, there's also been interest in light or ultralight vehicles, capable of aerial transportation for small loads or passengers catering to specific needs. Over different periods, numerous projects in this category have emerged. For instance, one of the early endeavours to create a flying jeep for military applications was the development of the XV-8 Fleep by the American company Ryan. In response to the diverse transportation needs of the military, including the requirement for aircraft capable of transporting light loads or small groups of personnel, Ryan Aeronautical Company initiated work on its version of such an aircraft in the late 1950s. This project incorporated several innovative ideas aimed at reducing the weight and size of the structure while meeting the necessary flight and carrying capacity requirements. Designated as the XV-8, the aircraft project was informally dubbed FLEEP, or Flying Jeep. However, official military documents refer to it as the FWAUV, Flexible Wing Aerial Utility Vehicle. In other words, auxiliary air transport with a flexible wing. Notably, the official designation mirrored the aircraft's goals and fundamental design features, while the informal name encapsulated its operational essence. To achieve the desired characteristics, the prospective aircraft needed to minimize weight. A solution proposed was to utilize a flexible wing, commonly known as a wing rogolo, to reduce the structure's mass. Back in 1948, Francis and Gertrude Rogolo proposed an original wing design suitable for use in light aircraft. It was originally proposed to use a frame of 3 parts of great length, to which it was necessary to fix a square or diamond-shaped canvas. In the future, a new design of such a wing appeared, featuring a different composition of the power elements and the triangular shape of the canvas. The transition from traditional rigid wings to the Rogolo system in the Ryan XV-8 project was notable for its simplicity and cost-effectiveness in production. One characteristic feature of this aircraft was its ability to control flight by adjusting the relative position of the wing and the aircraft's center of gravity. However, the flexible wing also had its limitations, particularly in adverse weather conditions, which could restrict its operation in certain environments. Nevertheless, the Rogolo wing later found application in hang gliders. In the XV-8 project, the Rogolo wing was proposed for use, along with several other components serving various purposes. The unique characteristics of the wing, along with existing requirements and new ideas, contributed to the development of a complex aircraft structure capable of transporting people or cargo despite its simplicity. The fuselage of the XV-8 aircraft featured a straightforward design with essential components. A rectangular platform served as the basis, equipped with fixtures for cargo installation. Positioned in front of the platform was a small protruding unit housing the controls and pilot's seat within a nose cone. At the rear of the platform, a frame was provided for mounting the engine. Supporting structures, both in front and behind the platform, were attached to accommodate the unusual design of the wing, with additional components for wing control integrated into these structures. Ryan Aeronautical developed its own version of the flexible wing for use in the XV-8 project, contributing to the aircraft's unique design and capabilities. As a basis for this product, 3 metal pipes with a length of 26 feet, about 8 meters, were used. In the nose of the wing, 3 tubes were pivotally connected, which allowed them to move in the same plane. A special mechanism was used to change the relative position of the pipes of the wing frame, which implies the simultaneous movement of the side parts. Near the central part of the wing was placed a set of rigid beams, with the help of which the side pipes could be reduced to the central or conversely diluted to the sides. At maximum extension, the wingspan of the XV-8 exceeded 10 meters, while when folded it measured 3 meters. To manage the excessive spreading of the tubes, a control mechanism and several braces were employed. The wing structure comprised 3 pipe beams supporting a quadrangular canvas, forming the wing plane and generating lift. Upon extension, the side pipes created the characteristic wing profile with 2 curved sections at the rear. The leading edge exhibited a sweep of 50 degrees, and the total area, excluding canvas bends, measured 450 square meters. Various materials, including synthetic textiles and films, were tested for the canvas surface. Mounted on the central beam of the Rogolo folding wing were attachments for fuselage truss installation. This pipe was firmly affixed to a swinging arm hinged at the apex of the framework. The front arm of the rocker was linked to a system of rigid rods leading to the control post. Using the appropriate lever, the pilot could adjust the wing's angle of attack to suit the current flight conditions. Located at the rear of the fuselage was an engine mounting frame. The power plant employed was the Continental IO360A piston aircraft engine, delivering 210 horsepower, paired with a 2-bladed propeller with a diameter of 2.14 meters. During testing phases, the XV-8 FLEEP underwent trials with and without engine covers for varying aerodynamic conditions. A substantial fuel tank, contributing to the vehicle's bulkiness, was situated in the central portion of the wing truss. To enhance aerodynamics, a vertical tail was integrated into the design. Mounted on a lightweight beam extending from the engine frame to the fuselage platform, a trapezoidal keel was attached, with its upper section pivotally connected to the central beam of the keel. The beam was designed so that when the angle of attack of the wing changes, the keel remains upright. There were drives to rotate the keel around the vertical axis, which it was proposed to use to control the course. For the transport of goods or passengers in the Project FLEEP FWAUV, it was proposed to use the platform in the central part of the fuselage in close proximity to the center of gravity. The length of the cargo platform reached 2 meters, the width was slightly less at 1.5 meters. The Ryan XV-8 FLEEP project aimed at maximizing the reduction in size and weight of the aircraft design, and it appears this objective was successfully achieved. The dimensions of the vehicle were kept compact, with a length not exceeding 8 meters, a wingspan of 10 meters when deployed, and a parking height of 4.4 meters. Folding the wing allowed for a reduction in the overall width of the aircraft to about 3 meters while maintaining other dimensions. The aircraft's own weight was a mere 506 kilograms, 1,115 pounds, emphasizing its lightweight construction. For flight preparation, it was suggested to load 68 kilograms, 150 pounds of fuel into the 6.8 kilogram, 15-pound tanks. With fuel and the pilot accounted for, the minimum flight weight of the flying Jeep was estimated at 658 kilograms, 1,450 pounds. This left a payload capacity of 385 kilograms, 850 pounds, resulting in a maximum takeoff weight of 1,043 kilograms, 2,300 pounds. To facilitate takeoff and landing, the aircraft was equipped with a simple non-removable landing gear. The cargo area between the wing trusses could accommodate standard ammunition boxes or weapons, and there was also space for several soldiers with their gear. The landing gear featured light trusses with vertical uprights at the corners of the cargo area, each fitted with a wheel, with telescopic shock absorbers based on springs. In 1961, the development company constructed a full-size model of the XV-8 FLEEP aircraft and subjected it to wind tunnel testing, during which no significant issues were encountered. This suggests a promising outlook for the project's development and potential deployment. The proposed appearance of the machine allowed to fly, and the combined control of changing the position of the wing and keel could give the desired maneuverability. According to the results of the tests in the wind tunnel, it was recommended to continue the work and begin a full test on the airfield. For use in testing, the first prototype was built with the serial number 6313003. It was built on the original project and fully consistent with the above description. The initial prototype of the FLEEP, distinguished by its characteristic appearance, underwent successful runway runs without any issues. However, challenges emerged during attempts to lift the flying Jeep into the air, highlighting both its strengths and weaknesses. To achieve takeoff and landing, a runway length of 170 meters was required, demonstrating the effectiveness of the wing's optimal angle of attack. However, this design feature proved to be a drawback in other flight modes, as swinging the wing and adjusting its angle of attack didn't provide the necessary control. The lack of adequate control in flight could potentially lead to serious consequences, particularly considering the intended military application of the equipment. Consequently, the XV-8 project required significant improvements to address these shortcomings. Further analysis identified necessary enhancements, including simplifying the wing's angle of attack control system to allow fixation of the central tube in one of two positions. Additionally, the updated design necessitated the incorporation of a complete tail with a set of control surfaces to improve maneuverability. The revised project aimed to meet these new requirements while preserving the compactness and lightweight characteristics of the aircraft's structure. Consequently, a second prototype, identified by the factory number 6313004, was promptly constructed according to the updated specifications. In accordance with the updated requirements, the second machine FLEEP FWAUV received a new version of the power elements of the wing. The three pipes were now connected by a transverse truss consisting of several separate elements. Instead of a complex structure mounted on the fuselage, a set of racks of a simplified design was used. At the same time, the hinge was kept to change the angle of attack of the wing. It was decided to streamline the design of the aircraft further by replacing the four-point chassis with a more simplified configuration, opting for a single central location for the front struts. Additionally, the traditional keel was eliminated, making room for more sophisticated components. The revised tail configuration featured two inclined planes, forming a V-shaped tail on the elongated tail section of the fuselage platform. These planes housed fixed components as well as pivotally mounted parts that could function as rudders. By synchronously or differentially deflecting these rudders, control over roll or yaw could be achieved. Another controlled surface, acting as the elevator, was positioned on the rear edge of the fuselage platform. In the updated Ryan XV-8 fleet project, it was proposed to utilize changes in the wing's angle of attack solely during takeoff and landing. During horizontal flight, the wing would remain fixed in the appropriate position, with control primarily relying on the tail rudders. Prototype number 6313004 underwent testing, affirming the effectiveness of the modifications implemented. The handling significantly improved, reducing the risk of accidents. This advancement allowed for comprehensive flight tests to establish the machine's characteristics. The second prototype demonstrated a maximum flight speed of 96 km an hour, with a cruising speed slightly below 90 km an hour and a flight range of 193 km. With successful test results, the project's future prospects were determined, indicating promising potential for further development. A characteristic feature of the first version of the Project XV-8 FWAUV was the maximum possible simplicity of the design, which allowed good weight returns to be achieved. Noticeable refinements of the device necessary to increase manageability and reduce the likelihood of an accident led to some increase in its own weight and a corresponding decrease in other parameters. In conclusion, despite its initial promise, the Ryan XV-8 fleet project didn't meet the expectations of the potential military customer due to shortcomings in controllability and performance. The first version lacked adequate controllability despite its advantages in size and cargo capacity, while the second version sacrificed certain parameters in favor of improved controllability. Recognizing the limitations of the existing design, further development of the XV-8 project was deemed impractical, leading to its closure. However, the flexible wing used in the project showed great promise and potential for various applications. Despite its simplicity, the Rogerlow wing design proved to be of significant interest and paved the way for advancements in ultralight aviation. Although the XV-8 project didn't achieve tangible results in military re-equipment, it played a crucial role in advancing the understanding and development of flexible wing technology, contributing to future innovations in aviation. During the Cold War, the US Army was actively exploring various aviation technologies to gain an edge over the expanding threat posed by the Soviet Union. The VZ-4DA, also known as the Model 16, developed at Fort Eustis, was one such result of this era. Edmund R. Doak, the president of Doak Aircraft Company in Torrance, California, had been experimenting with ducted fans and related air-moving concepts since 1935. He proposed a vertical takeoff and landing VTOL aircraft to the US military as early as 1950. Doak successfully convinced the Army Transportation Research and Engineering Command at Fort Eustis that his VTOL aircraft could amalgamate the benefits of a conventional fixed-wing fighter with the helicopter's capacity to take off and land in confined spaces. Recognizing the potential vulnerability of Allied air bases and runways to Soviet first strikes, the Army considered the ability to take off and land in small areas crucial. VTOLs, similar to helicopters, offered the advantage of lingering longer over a target, hovering and even flying backwards. In essence, the Doak Model 16 appeared to be an ideal utility and observation platform with the potential to deliver fire to ground targets. On April 10, 1956, the Army awarded Doak a contract for a single research vehicle, initiating the development of the experimental VTOL aircraft. Only one prototype, serial number 569642, would ever be built and tested. The Doak 16's two 5-foot diameter ducted fiberglass fans were located on its wingtips. Positioned vertically for takeoff and landing, they were rotated into a horizontal attitude for normal forward flight, the first time this concept was successfully employed. A rotation speed of 4,800 RPM was required to achieve lift. To maintain a low weight, the fuselage of the Doak 16 was constructed using uncovered welded steel tubing, later covered with molded fiberglass at the nose and thin aluminum sheeting on the aft fuselage. This modification was made when it was discovered that the open frame was hindering forward speed trials. The wings and tail, on the other hand, were made of metal. Edmund R. Doak demonstrated resourcefulness in cost-cutting measures, incorporating the landing gear from a Cessna 182, seats from a North American F-51, and duct actuators from Lockheed T-33 electric flap motors. The two-place tandem cockpit could accommodate a pilot and observer, with standard stick and rudder controls for the pilot. The aircraft's empty weight was 2,400 pounds, and its gross weight was 3,300 pounds. It had a wingspan of 25 feet 7 inches, measured 32 feet in length, and stood 10 feet 1 inch high. By 1958, the Doak 16 had undergone multiple test flights at Torrance Municipal Airport. Its first hovering flight took place on February 25, 1958, and on May 5, 1959, the prototype achieved its first conversion from vertical to horizontal flight, and vice versa. The Doak 16 completed 50 hours of flight testing, including 32 hours on a test stand, 18 hours of tethered hovering, and taxiing. Throughout this process, some undesirable flight characteristics emerged, such as the aircraft's tendency to nose up during the transition from hovering to forward flight, and a short takeoff and landing performance that fell below expectations. But engineers believed these problems were all solvable. Transferred to Edwards Air Force Base in October 1958, the Doak 16 underwent another 50 hours of testing, in the course of which it logged some promising performances. The VTOL single 825 horsepower Lycoming T53L1 turbine power plant gave it a maximum speed of 230 miles per hour, a cruising speed of 175 miles per hour, and range of 250 miles. A T-box on the engine transmitted power to the ducted fans through a 4-inch tubular aluminum shaft and two smaller steel shafts. The aircraft's service ceiling was 12,000 feet, and it had a flight endurance of 1 hour. These performance attributes led to its acceptance by the Army in September 1959. Officially designated the VZ-4DA, the prototype was then transferred to NASA Langley Research Center in Hampton, Virginia, for further testing. In late 1960, a recession in the aerospace industry prompted Edmund Doak to lay off 90% of his employees. During this period, Douglas Aircraft took over the VZ-4DA project by purchasing the patent rights and engineering files. 4 Doak engineers were also hired by Douglas to continue their work at El Segundo. They implemented a larger engine and made structural improvements. However, after 3 more years of testing, the Army withdrew the VZ-4DA from active trials. NASA subsequently acquired it in 1973, and it was later transferred to Fort Eustis, where it remained in storage for a time. The demise of the VZ-4DA as a viable Army aircraft can be attributed to the evolving preferences within the Army. As the helicopter emerged as the Army's preferred mode of transport during the Doak 16's development, the focus shifted to funding rotorcraft, leading to a reduced emphasis on unconventional prototypes, including the VZ-4DA, which were previously under consideration for production. The changing strategic priorities within the Army contributed to the discontinuation of the VZ-4DA as an active military aircraft.
It is a historical discovery worth its weight in gold. A truly important document of German aviation history is uncovered. It is not found in the archives or by any secret military personnel after the war. It happens instead by accident. On an ordinary day for this factory worker, he discovers a sealed canister containing a drawing. It appears to be a blueprint for the design of an aircraft. On closer inspection, the document dates back to the mid-1920s. What it turns out to be are the workings of a deadly state-of-the-art bomber, illegal in Germany at that time. Its origins are inspired by this strangely designed plane. It may look backwards, but the logic behind the design is truly forward in thinking. It is one of the original tail-first, canard-designed planes, and the concept behind it demonstrates Germany's desire to be at aviation's vanguard.
In the Ente, again the duck, late 20s, they had this design. Tail first, not really an airliner, but a few seats. The tail first design would allow you to triumph against the stall. The stall was very much a feared thing. You lose control, you crash. A canard, a tail first design, can say that if forward tail stalls, nose goes down, pick up speed, airplane stays in the air, all is well. The prototype flew around 1927-28, worked quite well.
It is an unconventional design by an unconventional designer. Heinrich Fokker is hoping to remove one of the pilot's biggest concerns since the birth of aviation, the dreaded stall factor. Thus, the design is catching the attention of aviation enthusiasts from around the world. Innovative as the F-19 may be, it is not without its flaws.
Eventually, it crashed. If you lose control of it at low level, it's deadly. And Mr. Wolf, the Wolf of the Focke-Wulf, he's the one who died in the crash.
With the death of their founder, and with military aircraft strictly forbidden in Germany, those at Focke-Wulf are now at a fork in the road. Do they keep on developing canard technology for peaceful and, most importantly, legal purposes? Or do they risk both the company's future and their freedom by turning it into a deadly weapon of force? In an extremely risky decision in the history of the company, the plan for the F-19 dramatically changes. Instead of being the originally planned sports plane, it is now going to be a deadly bomber, capable of causing tremendous havoc over Europe's skies. The man behind this madness is one of Germany's true engineering geniuses, Kurt Tank, who joins Focke-Wulf as a result of a company takeover. Being there every step of the way, he harnesses and perfects this technology into what becomes known as the Model 42. The source of funding for this ambitious project in an economically starved country is still unknown. However, there is one thing for certain. Germany's quest to rule the skies is something neither military defeat nor monetary limitation can stop.
Tail-first design was developed for a number of reasons. If you have a canard configuration, you have a very thin nose because your engine is behind the pilot. You can technically, at least in theory, increase speed with the same amount of power, which is good for combat aircraft. Also, because you have a fairly thin nose, you can improve, to a certain extent, pilot visibility.
When completed, this aircraft, powered by BMW's V12 engines and possessing a maximum speed of 200 miles an hour, is for Germany both her sword and shield. Any potential enemy will think twice about pushing around a Germany possessing an arsenal of aircraft carrying 20 200-pound bombs on board. More importantly, if Germany desires to reclaim her lost territories following the Treaty of Versailles, the Model 42 can put immense fear into both Europe's citizens and industries with its capability of causing enormous destruction. As testing rapidly advances, ironically, the rug is pulled from underneath them by neither pacifists nor neighboring European powers, but by the most militaristic regime in history. As Hitler's Nazi Party comes to power in 1933, the newly installed Chancellor's main interests are in maintaining and consolidating his power. An illegal aircraft project, if discovered, could be the end to his fragile rule. As a result, the project dies alongside German democracy. Although the Model 42's future is ended with the single stroke of a pen, the concept of canard technology lives on. Focke-Wulf obeys the government's decision, but at the same time rapidly develops what is known as short takeoff and landing technology. One of its crown jewels is the FW-61, the world's first fully controllable helicopter. Its creator, Professor Heinrich Fokkers, much like his German predecessors, symbolizes that an idea can never be defeated, no matter what obstacles it may face. Had this bomber plane been approved for production on a massive scale, one can only imagine what impact it would have had on the Second World War. It is one of the conflict's greatest what-ifs. In fighting both Britain and the Soviet Union, it might well have tipped the scale in favor of Germany. The Model 42 thus may have resulted in a soaring victory and changed dramatically the outcome of the war in Europe.
I name you hero and wish you good luck and Godspeed to all who fly in this type. Yeah? Thank you very much.
Despite the enthusiasm at Handley Page, the mood in England at this time is anything but cheerful. By 1937, the drums of war are beginning to be heard across the nation. Never has this been more evident than at these factories, where the Harrow is being introduced in an attempt to showcase Britain's military power. Unfortunately, it is technologically years behind the now cancelled Model 42. With $400 million being spent on aviation in a single year, the government assures its citizens that they have nothing to fear with this powerful weapon on their side. However, the question remains as to whether these bombers can stand up to the growing German threat. These fears are finally realized as Britain's cities are repeatedly bombed by the Luftwaffe, causing enormous destruction and loss of life. The Blitz has now focused the world's attention to what the bomber is capable of doing. The nation everyone is looking to is in dire need of a solution to this deadly problem. It may be one of Britain's most unusual designs for a plane. At Miles Aircraft, this prototype, known as the Libellula, marks not only the resurrection of the canard design, but also exemplifies a company truly thinking outside the box.
People were very appreciative of the fact that Miles had this wonderful innovatory streak in them, and that they might come up trumps with something.
During the war in Reading, Berkshire, the factories of Miles Aircraft are working overtime, making a substantial contribution to the nation's war effort. What is capturing the imagination of the company's top designers is the reconstruction of a revolutionary aircraft. A plane that will capture massive attention with a design so futuristic that it is years ahead of its time. Hard at work with their initial sketches by ambitious and intelligent designers, the canard plane is reborn. In this factory, British men and women are side by side, hard at work putting together this complicated design. While their soldiers are fighting on the front lines, these workers have stayed behind. Their job is to maintain the production of wartime equipment on the home front. And a mighty task for them is to construct this unusual plane possessing a tandem wing arrangement, requiring countless hours of labor. Unlike standard aircraft, the Libellula M35 has its wings at different heights and at different lengths. The reason for this is that the lesser wing acts as a forward-mounted stabilizer, thus improving control, especially in regards to landing. With its shorter wingspan and not requiring them to fold, when completed, the M35 is to be used as a carrier-borne naval fighter. Its sister plane, the second of the Libellulas, with an additional engine, is intended strictly for bombing purposes. Its creator, George Miles, says that when completed, the plane will resemble a dragonfly. In just 90 days, the first plane is built, remarkable for its time. Those at Miles Aircraft are determined to see what this plane can do once it is up in the air. Getting the plane ready for flight, engineers are putting the Libellula in position. As the final inspections are being conducted both underneath the plane and in the cockpit, the company, having a huge investment in the aircraft's success, hopes to put it into mass production shortly, pending government approval. Possessing a tricycle landing gear, the intent is to achieve complete stability when landing. At the rear of the wings are the corresponding vertical and horizontal stabilizers and rudders. Once in the air, the plane is able to fly at 160 miles an hour and climb at a rate of 1,100 feet a minute. Its canard features lend the aircraft well to both high and low-speed flight. With all of its advantages, however, the Libellula is not without its drawbacks.
So the Libellula, the problem was to control the aircraft for takeoff and landing. It had 2 sets of flaps with 5 settings for each set. So you had a potential 10 combinations. This was difficult because getting the right combination was one thing, because every time you changed the combination, it had some effect on the controllability of the aircraft. And it was really impractical.
Complexity becomes its Achilles heel. And despite the optimism from those involved in both the flying and the making of the plane, the military situation at the time dictates that the Libellula must come in for a political landing. In many ways, it is surprising that both versions of the design never go into mass production. However, its fate, similar to that of the Model 42, rests not on the aspiration of its designers, but on external circumstances. Britain, now with the United States and the Soviet Union as allies, is turning the tide against the German war machine. As a result, the demand for the Libellula evaporates. With prospects for the canard design now looking all but dead, miraculously, it once again is resurrected. This time, however, it is not done by any European power. Instead, it is done across the Atlantic Ocean, in America, the birthplace of aviation. Here, the canard design is reincarnated. The United States, referred to by Japanese Admiral Yamamoto as the sleeping giant, has awakened. Having an industrial capacity second to none, geography is the country's greatest asset. A massive labor force working uninterrupted without fear of factories being bombed is Uncle Sam's greatest advantage. And aircraft production is no exception. In terms of quantity, the United States is the undisputed champion. No European nation can even come close to their rate of production. However, while the country leads in quantity, it is quality that one aircraft company aspires to excel at.
But there was definitely a potential there. So Lockheed started to look at what kind of airplane could be designed around a turbine engine for high-performance aircraft.
It is Lockheed who believes it has the jet-powered solution for the fighter. One of its most secret projects of the war is the L-133 prototype, which is tested to see if this new technology can be harnessed into something tangible for the United States military. Thus, the canard design, an important component of the project, rises from the ashes. At first, the Army Air Force show interest in the project. The emerging military-industrial complex, however, dictates the final decision, with it becoming a case of quality versus quantity that ultimately determines the project's future.
They looked at it and sort of, well, this is all very interesting, but you have an engine that's a wee bit on the complicated side, and you're producing Hudsons for the Brits, Lightnings for us, you're producing light transport aircraft, and in some cases, like Lightning, for example, your deliveries are good, but may not be quite as good as we would like them to be, and you want to get involved in the design of a new type of engine and a new type of aircraft. Please slow down. Our enthusiasm is not necessarily there.
With war raging on in both Europe and the Pacific, a policy of producing what is known and reliable is enacted. Every second must be accounted for. With the possibility of the model not functioning properly, precious time must not be spent testing the unknown. Thus, the L-133 becomes, much like the Model 42 and the Libellula, an aircraft whose potential remained unfulfilled. There is no doubting, however, with its state-of-the-art technology, the development of the L-133 would have brought canard technology to a new level. It is the right place, just not the right time for Lockheed. To the employees at Curtiss-Wright and canard enthusiasts, deliverance has arrived with the XP-55, known as the Ascender. With the main wings located at the tail end of the fuselage, it is certain to attract attention due to its unique design.
Presenting the Army's new Ascender plane. With its elevator controls in the nose and its motor and propeller in the rear, this push-propelled fighter reverses conventional airplane design. Developed experimentally as the XP-55, the new plane gives forward vision for the pilot and a clear path for his gunfire. In action, the darting tail-first Ascender seems to fly backwards.
Its origins lie in an Army Air Corps flirtation with unconventional aircraft design. And nothing defines the unconventional like the tail-first plane. Despite a policy of turning out proven aircraft on a massive scale, there is some room for experimenting. Originally intended as a design to be powered by Pratt & Whitney liquid-cooled H engines, it is perhaps the best chance canard technology has of becoming more than just a blueprint or a workable prototype. Mass-scale production is the ultimate goal of its enthusiasts. After extensive testing, it appears that the Ascender is the best hope in achieving this goal. The Air Corps is impressed so far and asks for 3 prototypes to be built. The plane's future, however, comes crashing down with its first prototype. A stalling malfunction results in the first Ascender taking a 16,000-foot nosedive. As the company attempts to fix this problem, competing technology is evolving faster than XP-55. In the end, the project is cancelled indefinitely. It is not worth either the government's time or money to further pursue such a risky endeavor. Despite its name, in the end, the plane does nothing but descend into the depths of aviation history. By 1945, as Japan enters the 4th year in its war against the United States, the sleeping giant that Admiral Yamamoto feared would awake is now on his nation's doorstep. After massive casualties on both sides, American military power is successful in pushing back Japanese forces through both its superior air and sea power. The American mainland remains untouched after Pearl Harbor, with military production skyrocketing. Japan, a nation that seemed invincible in early 1942, is now feeling this incredible American force wreak havoc over its mainland. In particular, Japanese cities and their inhabitants feel the horrors of an air war that does not distinguish between military and civilian targets. American B-29s, leaving from the islands of Guam and Saipan, fly a total of 107 bombing raid missions on Japan's cities in just 1 year. One particular raid that takes place on the night of March the 9th destroys 250,000 homes and burns almost 100,000 citizens to death. In General MacArthur's historical report, he writes that the effect of these raids rocked the nation to its very foundations. With each passing month, the casualties keep escalating, with nearly 3 million people killed. Mass famine is spreading, with an estimated 10 million people suffering from serious malnutrition. Japanese Admiral Matomi Ogaki, writing in his diary on June the 18th, asks, "Does the enemy intend to destroy all of the cities in this country?" General Curtis LeMay, a key architect of this bombing strategy, pledges to bomb and burn them until they quit. The only problem for LeMay is that with a schedule of approximately 16 burn jobs on urban industrial areas every 3 to 4 days, by mid-August, American bombers will run out of cities to destroy. Japanese air forces are proving incapable of preventing this mass destruction of their homeland. A carrier raid in March of 1945 results in 161 out of 193 Japanese aircraft being shot down by American forces. Vice Admiral John S. McCain pledges to hunt down and destroy every damn plane in Japan. Despite the much-feared kamikaze tactics being employed by Japanese pilots, American military leaders are no longer planning the possibility, but the eventuality, of Japan's surrender. The maps being used by both the Joint Chiefs of Staff and the President show that whether it is through a ground force invasion or through the dropping of an atomic bomb, Japan is a nation on the brink of defeat. The only decision being made by the political and military leaders of the United States is which course of action they should embark on in order to achieve the goal of an unconditional surrender. To those Japanese military leaders who are in their last throes, their hope is to develop a highly maneuverable interceptor plane to act as an antidote against American B-29s. The Shinden aircraft, developed by Kyushu, is the only aircraft with a canard designed to be ordered into quantity production during the Second World War. Equipped to hold one pilot and having a wingspan of 36 feet, armed with 4 30mm cannons and a top speed of 466 miles per hour, in addition to its important canard features, the Japanese military is hoping that Shinden holds the answer to solving the problem of the B-29 bomber. Work begins in June of 1944 to develop this plane, whose name translates to Magnificent Lightning. By now, however, time is not something Japan has on its side. Although the first prototype of the Shinden flies on August the 3rd, it is simply too late to prevent a devastating American attack. 3 days after it is tested, the first atomic bomb is dropped on Hiroshima. 3 days later, the city of Nagasaki is dealt the same blow. With these two bombings, in addition to the Soviet Union declaring war against Japan, the demand of unconditional surrender is met on September the 2nd, 1945, marking the end to war in the Pacific. The story of the Shinden remains one of the greatest what-ifs in Second World War history. Had Japanese production and testing begun earlier, would this aircraft have been able to stop American bombing plans as hoped? If the jet technology for this aircraft arrived in time, would the Shinden have been to Japan what the Spitfire and Hurricane had been to Britain in its time of need? For it remains an unknown piece of canard history. The canard design, with its origins dating back to the Wright brothers and their first flight of 1903, is a story of aviation constantly having to overcome the barriers and obstacles put in its way. It is a story of emerging and innovative technology locking horns with the politics of its time. Whether it is a result of a new government taking power, the policies of production, or of a country in desperation, canard technology never soars above these barricades in the first half of the 20th century. There is no doubting, however, what canard technology represents in the history of aviation. It symbolizes the innovative spirit, and it symbolizes the proud heritage of aviation. The canard design is to be remembered through its planes and by the people that created them.
August 6, 1945. The day warfare changes irreversibly. It is not the result of a battleship or a fighter plane. Instead, it comes from a device less than 10 feet in length and 3 feet in width. Dropped from a B-29 Superfortress, the bomb known as Little Boy is the first atomic weapon to be used in history. Alongside its accomplice, Fat Man, these two weapons of mass destruction pulverize the Japanese as two cities are obliterated. Now, the world led by the United States and the Soviet Union enter a new and frightening age where just one bomb can wipe out an entire population. With the Second World War ending and the Cold War beginning, America and the Communists start a massive buildup of this new technology. The race is on, where whoever possesses the most deadly arsenal of atomic force prevails. On both sides of the Iron Curtain, nuclear weapons become the ultimate symbol of strength and might. And during this period of intense Cold War anxiety, the idea of having aircraft fueled by this new source of energy is given the green light. If a nation can power homes and submarines with nuclear power, will planes be next? Having an atomic reactor on board has endless possibilities. Unlimited range, and the ability to be anywhere in the world in a matter of hours, ready to strike. Truly awesome aviation that will determine the #1 superpower. Unfortunately, this concept is easier said than done. Placing a nuclear device on an aircraft is both complicated and extremely dangerous. Can American scientists and aircraft designers overcome these obstacles? Can they prove the skeptics wrong? This is their story. The United States' decade-long saga to produce the first nuclear-powered aircraft. Prepare to experience the atomic-powered plane.
We are gathered here, representatives of the major warring powers, conclude a solemn agreement whereby peace may be restored.
With the Japanese surrender on the USS Missouri, Americans are both victorious and confident. The war they have been fighting for over 3 years has finally ended. They have emerged a superpower with what seems to be an unlimited industrial capacity. The nations of Europe are no longer the power brokers they once were. For it is the United States and its ally the Soviet Union that remained strong at the end of the Second World War. But just as this conflict ends, a new and more deadly struggle begins, as Nazism is replaced by communism as the greatest threat to Western democracies.
Nobody really knew a grand vision for Europe, even as Nazi Germany collapsed. There were still large questions as to territory, peoples, the movement of peoples, and exactly how this would all work out. The grand strategy with Franklin Roosevelt's the famous spheres of influence, which means nothing, everything and nothing at exactly the same time, and that's where the roots of the Cold War come in big. There was a lot of tension and a lot of questions on both sides as to how it would all work out.
With this shift in the balance of power, the Soviets are no longer America's ally. They are now the enemy. And for the next 50 years, tensions between the two superpowers are felt beyond the capitals of Moscow and Washington, D.C., as the world is divided between capitalist and communist. Whoever can win the hearts and minds of those around the globe will emerge victorious. As this new Cold War takes shape, people begin to realize that America's victory over Japan has become a double-edged sword. The dropping of an atomic bomb, the nuclear genie has been let out of the bottle.
Well, world reaction was stunned. I mean, this is, I think, even at the time and place, a realization that it was a monumental event, even though nobody really understood what had taken place scientifically or even politically, even with respect to the war, it was unclear. But I think most people understood, and my read of the press in particular at the time was an acknowledgement that this was really big. This wasn't just any sort of military adventure whatsoever. But it's important to keep in mind that almost nobody, including the men who made the decision to drop it and the scientists who worked on the project, understood its ramifications in full. And I think it's useful to, remember Einstein, right, saying, I don't know how they're going to fight this war, but I guarantee you how they'll fight the next with sticks and stones.
Fearing the Soviets will be next, Russian scientists begin a mad rush to acquire this technology. What the United States possesses, they must equal and better it. It is unlike any other arms race in history. The end result could potentially wipe out 1/2 of the world's population, and even more. For this reason, it is vital that both nations attain as much nuclear technology as possible to deter the other from striking. As a result, rigorous testing is done on both the American mainland and on strategic outposts like Bikini Atoll.
The B-29 Dave's Dream takes off from Vertiplane to deliver the bomb, equal to 50,000 tons of TNT, while an electric metronome counts the final seconds. Cover your eyes. Now, on the way.
To calm public fear of atomic power, every attempt is made by the United States government to emphasize the positive aspects of this new source of energy. Nuclear power plants are constructed across the country as a sign of progress and achievement. President Eisenhower goes to the United Nations with the idea of using atoms for peace.
The United States pledges before you, and therefore before the world, its determination to help solve the fearful atomic dilemma, to devote its entire heart and mind to find the way by which the miraculous inventiveness of man shall not be dedicated to his death, but consecrated to his life.
You have to understand the atomic aircraft project as part of the pentomic era. The 1950s, late 40s and early 50s, when everything that could be atomic was being turned into an atomic thing. There was atoms for peace. There was the idea that energy would be so cheap you couldn't meter it. You wouldn't have to meter it. Anything that could be powered by the atom was to be powered.
Despite these efforts, many are still skeptical about this source of power and its deadly ramifications. These fears are amplified with the development of Project Pluto, a nuclear-powered missile designed to unleash fission fragments all over the Soviet Union. Dubbed the Flying Crowbar, this weapon is considered too extreme even for the most hawkish Cold Warrior and is abruptly cancelled. Looking at the carnage of Hiroshima and Nagasaki, numerous Americans fear this technology throughout the 1950s.
What's it like, Chaplain? First of all, one sees a very, very bright light, followed by a shock wave, and then you hear the sound of the blast, and then it seems as though there's a minor earthquake. And then you look up and you see the fireball as it ascends up into the heavens. It contains all of the rich colors of the rainbow, and then as it rises up into the atmosphere, it turns a beautiful pale yellow, and then assembled into the mushroom. It's a wonderful sight to behold.
Hoping to end these concerns, in January of 1954, the USS Nautilus becomes the first naval vessel to safely enter the nuclear realm. With an atomic reactor powering the submarine, it can stay submerged for months if necessary, giving the United States a huge advantage over the Soviets in case trouble erupts. With this advancement, many are asking if it can work for an airplane as well.
And that's what somebody got the bad idea. Well, nuclear power, you can run a submarine, why can't you run an airplane?
Much will be learned here of the workings of atomic engines, not only for submarines, but for many peacetime uses as well. For passenger and merchant ships, for land transportation, for electric power plants, even perhaps for the huge airplanes of the future.
Submarines are not constrained by the same weight limitations as an airplane. So you could put a 10-ton reactor in with 100 tons of shielding, all wrapped around it in something that need only float. It's a completely different physics principle. And so therefore you have the space in the submarine for large reactors, large shielding, and large cooling systems.
It appears that what the Navy has been able to accomplish, the Air Force is going to have a harder time replicating. Despite all the doubts and skepticism, the decision to combine atomic energy with aviation is approved. Just like how the Liberators and flying fortresses that destroyed German cities mercilessly played an enormous part in winning the war in Europe, and how the constant bombardment of Japanese cities by B-29s was essential to American victory in the Pacific, perhaps a new bomber, powered by nuclear energy, will defeat the Soviets. For this reason, it comes as no surprise that many inside Air Force circles are eager to have a plane powered by the atom up in the skies as soon as possible. Across the Atlantic Ocean, the United States Navy hopes the same Anglo-American cooperation that produced the P-51 Mustang can result in their own version of a nuclear aircraft. Looking for the biggest plane Britannia can offer, both countries study the possibility of converting the gigantic Saunders Roe Princess flying boat, a plane whose time has passed, into a device given its second wind by nuclear power. A key advantage of this concept is its range. Just 1 pound of uranium-235 is the equivalent of over 250,000 gallons of jet fuel.
With the end of World War II and the start of the Cold War, they now needed a bomber that could reach the Soviet Union from the United States. A nuclear-powered aircraft would not be limited by a fuel load, so it was desirable from that point of view.
With 30 million horsepower, theoretically, the aircraft could be up in the skies far longer than any conventional bomber in the US's arsenal.
Would sort of loiter over somewhere, US soil, presumably for days or weeks on end, possibly. Sort of simply be there as a warning.
So despite fears of nuclear annihilation, both the Air Force and the American government approved the project to develop this plane. In May of 1946, the Nuclear Energy for the Propulsion of Aircraft, or NEPA, is created, where in the secret atomic city of Oak Ridge, Tennessee, the first stages of development begin. Looking for a company to start testing, Washington goes to one of its very best, Convair, makers of the massive B-36 Peacemaker. They are awarded the contract to begin designing their version of the atomic-powered plane, which after more than a decade of research and development, they dub the NX-2, an aircraft that looks eerily similar to North American Aviation's B-70 Valkyrie. The question is whether they'll use a B-36 or the new revolutionary jet-powered B-60 to begin their preliminary tests. An act of divine intervention makes this an easy decision for Convair when a tornado rips through Carswell Air Force Base, damaging a fleet of Peacemakers. With little to lose, it is after this natural disaster when the choice is made to repair one of the B-36s, named the Crusader, and turn it into a nuclear-powered bomber under the Plan X6, with the General Electric Corporation chosen as the company to build its reactor.
The US Air Force had a nuclear reactor installed aboard a Convair B-36 bomber. The nuclear reactor did not fly the aircraft. It had its own engine. It was simply there as an experiment to see, for example, the thickness of shielding required to protect the crew from long-term exposure to radiation.
A key roadblock in the plane's development comes from the radiation it will emit. Anyone standing within 100 feet of the core reactor unprotected is in store for a lethal dose of radioactivity. On land, nuclear power plants are shielded by more than 6 feet of concrete. In the skies, however, this shielding is too heavy for any aircraft, including the B-36, to sustain.
The single largest problem with an atomic-powered aircraft is that a reactor requires much shielding. Roughly for every ton of reactor, you require 10 tons of shielding. This was the case in the NV-36 program. A relatively small reactor required a cockpit shielded with 12 tons of lead and lead crystal glass, just to protect the crew from the radiation emitted by the reactor.
And for it to be economically feasible, it must be able to carry a payload bigger than the B-52. For nuclear aviation to become reality, these barriers must be overcome by its designers. With this in mind, Convair's still unbuilt NX-2 places its pilots and crew far away from the reactor, hopes that less shielding will be required. But even if this is accomplished, there are still questions surrounding the heat generated on board the plane. producing more radiation than a nuclear power plant into such a contained space has scientists worried that the intense temperatures are going to melt away the aircraft's interior.
There was no real way at the time to fix these problems, much as there isn't now. The shielding still grossly outweighs the reactor, and it turns out there's really no need for it.
Just like the Navy and its Princess flying boat, the Air Force is slowly realizing that the plane and the atom don't mix. Adding to these problems is many people's fear with all things nuclear. With the possibility of an entire city being wiped out with the flip of a switch, there are grave concerns over what happens if the plane crashes. If a hot reactor falls on a heavily populated area, the civilian casualties could be enormous. With this in mind, every precaution is taken when the NB-36 is sent out on a test flight.
We had a B-50 as a chase airplane to follow us in flight. Then they decided if we had to, for instance, an accident, what were we going to do? Well, they decided we got to have some paratroopers to follow them down. We had C-19 to carry paratroopers. And we landed. All of this was secret.
Eventually, for a number of reasons, safety, cost, practicality, the nuclear-powered aircraft never got off the ground.
With this concept all but dead, it is miraculously brought back to life when a report surfaces that the Soviets are building their own version of an atomic-powered plane, in the form of a modified Tupolev 95.
One of the big pushes for this project happened after the NB-36 had stopped flying. In December 1958, the very important magazine Aviation Week, now called Aviation Week in Space Technology, published an editorial with photographs that they said were of an atomic-powered aircraft being flown in the Soviet Union. They had these drawings that even showed the big red stars on the side of the aircraft. Turned out to be a complete falsehood, a complete lie, and it's now thought that it was put out by the contractors and the Joint Committee on Atomic Energy, who were trying to push the atomic aircraft program through Congress and to force the U.S. Air Force to accept it.
Many of the cutbacks have not been justified. I would not want to condemn all. I know one which I regard as very damaging indeed, the cutback and the stretch out of the atomic airplane program. If our technicians were permitted the money and the authority to go ahead, they could fly an atom plane next year. Under the Take It Easy program of the administration, however, we are not scheduled to fly an atomic plane before 1964, if then. I doubt if the Russians will wait that long.
Afraid of another Sputnik, the American government assures its people that with each passing year, a nuclear-powered aircraft becomes more of a reality. While behind the scenes, its designers know the project is impossible to achieve. One major blow comes from President Eisenhower, who fights to end this plane before it consumes hundreds of millions of dollars more in appropriations. But perhaps the biggest nail in the NX-2's coffin comes from a Boeing -80 prototype.
In 1957, the last year that the NB-36 was flown, the U.S. Air Force introduced its first KC-135 tankers. 3 years later, they had 400 of these aircraft, servicing as airborne refueling stations for B-52s. They could now reach any part of the Soviet Union from the United States without landing. The idea that you now needed a reactor to do this was over, and the U.S. government realized the project was essentially dead because they already had the bomber force that they wanted.
With KC-135s and B-52 Stratofortresses, by the end of the 1950s, patience is wearing thin for a nuclear-powered bomber. After spending more than $500 million, and with no end in sight, the project is now on the chopping block. As one politician is overheard saying, it has been marked by a lack of well-defined objectives and by administration indecision. The optimism of the late 1940s and early 1950s has vanished. And when a Defense Department official tells the media that the plane's price tag will be over $10 billion when finally completed, the NX-2's days are numbered.
The world is very different now.
In 1961, as the Eisenhower era ends and John F. Kennedy is sworn into office, the project receives its final nail in the coffin when the aircraft, like many other Cold War creations, is terminated.
At the end of the day, heavy atomic reactors don't really belong on aircraft. And aircraft with refueling can reach their targets anywhere in the world. A reactor was simply found unnecessary to do the job the US Air Force wanted to do.
Like many other Cold War concoctions, the atomic-powered plane represented thinking big. During a time when many thought that nuclear energy was the future for transportation, it was almost inevitable that an endeavor of this magnitude would be undertaken. With America and the Soviets on the brink of complete annihilation, aircraft like these were given the go-ahead, despite its impossibilities. In the end, the atomic-powered aircraft became the quintessential example of a military-industrial complex run amok, where profits were placed above people, and where Convair was placed above common sense.
The Miles aircraft concern conceived the M39 Libellula during the early 1940s, amid the turmoil of World War II. Initially, the concept aimed to simplify landing aircraft on carrier decks, addressing visibility challenges caused by forward-mounted engines and large wing mainplanes. A novel tandem wing arrangement was pursued to mitigate risks, resulting in a series of concepts explored by Miles during the war. The overarching term for these Miles designs was Libellula, named after the taxonomic family of the dragonfly. The groundwork for this project began with the M35, essentially a technology demonstrator for a single-seat naval fighter. Miles pursued this endeavour independently, using the tandem wing setup to reconfigure the centre of gravity found in conventionally configured military aircraft. In a brief span of 6 weeks, Miles engineers introduced the M35. This aircraft was equipped with a single de Havilland Gypsy Major air-cooled inline engine, boasting 130 horsepower. During testing, the engine exhibited temperamental behaviour and longitudinal control was problematic. Nevertheless, this design provided valuable insights into the unconventional arrangement, contributing to future developments in the field. Building on this knowledge, a new design emerged, scaled at 5/8 and designated as M39B. This single-seat demonstrator featured a pair of de Havilland Gypsy Major IC air-cooled inline engines, each with 130 horsepower, showcased in outboard nacelles beneath the rear wing mainplanes. The frontal mainplane was now positioned low against the sides of the cockpit, and the fuselage boasted a finely contoured shape from nose to tail. The undercarriage transitioned to a traditional tricycle configuration. Given the larger scope of the M39B project, its dimensions were appropriately increased. The wingspans now measured 25 feet at the front set and 37.5 feet at the rear. The overall length extended to 22.3 feet, and the maximum weight rose to 3,200 pounds. As constructed and tested, the M39B achieved speeds of up to 166 miles per hour thanks to its twin-engine setup and tandem wing approach. The maiden flight for the M39B occurred on July 22, 1943. A dorsal fin was later fitted at the fuselage aft for additional control to complete the M39B's iconic 3-finned appearance. Up until September of 1943, all of the work on the two aircraft, M35 and M39B, was as a private venture. From then on, the British Air Ministry decided to offer a formal development contract to Miles. Shortly after, Miles sought interest from the United States Army Air Forces, aware of their consideration of the domestic Curtiss XP-55 Ascender, which shared a tandem wing pusher engine configuration and was intended as a fighter. The USAF's response revealed a general lack of interest in the Miles product, as the XP-55 itself faced issues, particularly with stalls and recovery. The American program only progressed to flight testing, producing 3 aircraft in total. The M39B underwent evaluation at the Royal Aircraft Establishment, encountering problems from the outset. A new undercarriage had to be installed, and several accidents necessitated constant repairs, keeping the aircraft grounded for extended periods. Despite its unconventional arrangement, overall handling characteristics were considered normal. While landing and takeoff required adjustments to the standard routine, these were deemed forgivable, and stalling and recovery performed as anticipated. In 1941, the RAF issued a new specification for a medium-class, medium to high-altitude, high-performance bomber. Miles responded with its M39 project, a modified version of the M39B featuring a pressurized cockpit for a crew of 3. The proposed power for the M39 project included either 2 Rolls-Royce Merlin 61 series inline engines or 3 Powerjets W2500 gas-powered turbine engines. This design featured a significant wingspan increase, measuring 37.5 feet at the frontal wing and 55.8 feet at the rear pairing. The overall length expanded to 35.9 feet, and the maximum weight surged to 26,750 pounds. The envisioned cruising speed was 360 miles per hour, and armament was planned to include 2 20mm cannons in the wing roots, 1 gun per root, along with an internal bomb bay in the fuselage, capable of carrying up to 6,000 pounds of bombs. Ultimately, the de Havilland DH-99 Vampire fulfilled the specified requirements. The Hawker P1005 also competed for a period. Although a prototype M39 high-speed bomber was ordered under a November 1943 contract, it was never constructed. The RAF's bomber needs were met elsewhere, leading to the termination of the M39 project, along with the data-collecting M39B aircraft. While surviving the war, the M39B lasted only until 1948, when it was scrapped. Despite its shortcomings, the Miles Libellula left an indelible mark on aviation history. Its bold, unconventional design inspired future aircraft engineers to think outside the box and take risks. The Libellula remains a testament to the power of human ingenuity and the boundless potential of innovation. The Miles M39B Libellula serves as a fascinating case study of a daring, experimental aircraft that ultimately fell short of expectations. Its unique design, ambitious goals, and ultimate cancellation offer valuable lessons for future aviation endeavours. Originating from a design philosophy dating back to 1930, but conceived during the Second World War, the XCG-16 glider emerged as one of the most unconventional and innovative glider concepts ever tested. Initially designed for transporting heavy equipment and supplies, including vehicles and military personnel, the XCG-16 later became involved in experiments to deliver fuel to long-range bombers during flight. As a crucial element of the war effort, it showcased the capability to transport substantial loads without the need for an engine. Despite its troubled test history and eventual exclusion from production, the XCG-16's design retained its distinctive features. The roots of the XCG-16 can be traced back to May 1930, when American aero engineer Vincent Bernelli explored various lifting theories and flying wing concepts. The United States Army Air Force subsequently issued a specification calling for a novel design incorporating Bernelli's patented lifting fuselage concept. To assess the most suitable design for military use, a competition among different aircraft manufacturers was organized at Wright Field. Designers Hawley Bolus and Albert Kriz utilized Bernelli's concept as a foundation to create their own glider for the competition. Bolus, previously focused on designing leisure aircraft and recreational vehicles for the civilian market, ventured into military aircraft design for this competition. His most notable design had been the Bolus Road Chief, the trailer and caravan upon which Airstream had based their famous design. He'd also worked as one of the consultants on the Spirit of St. Louis, the aircraft piloted by Charles Lindbergh, who completed the first non-stop transatlantic flight between New York and Paris. Despite lacking experience in combat and military design, Bolus moved forward with his concept, collaborating closely with Kriz and the team at his company, Bolus Sailplanes. The German military's successful use of gliders during the 1940 invasion of Belgium, particularly in landing troops in challenging areas behind Belgian lines, drew attention. Gliders played a crucial role in capturing strategic sites, exemplified by the rapid overrun of Fort Aben-Amal in May 1940, where glider-borne Nazi soldiers surprised Belgian troops. While the United States initially maintained neutrality in the early stages of the war, experiences like the Battle of Fort Aben-Amal prompted the United States Army Air Corps to take gliders seriously into consideration. In response to the USAC's request for a glider capable of transporting troops, heavy equipment, and supplies towed behind engine-driven bombers and transport planes, Bolus and Kriz diverged from the traditional single fuselage design that characterized most American gliders. Instead, they embraced a flying wing concept, closely studying Bonelli's philosophy and incorporating their own ideas on top of it. A half-size prototype model was created in late 1942 by Bolus Sailplanes, with Bolus and his team considering the initial test results to be good. The first full-size glider prototype, named the MC-1 glider, was produced by General Airborne Transport. Following the closely followed design of the half-size model, initial factory tests once again indicated the potential of the new design. The full MC-1 design was envisioned to be larger than other gliders of its time. It was characterized by a high wing configuration with a wooden frame and fabric covering, all while retaining Bonelli's philosophy. With a wingspan of 110 feet and a length of 67 feet, the MC-1 boasted substantial dimensions. Bolus aimed for a cargo capacity of up to 15,000 pounds, facilitating the transport of both cargo and troops through two large cargo doors located at the glider's front for easy access and rapid deployment during battle situations. The intended operational method involved towing the XCG-16 into the air by a C-47 or C-54 Air Force transport plane, which would then release the glider to continue its flight independently. The glider featured a twin-boom design for the tail. Designed with spoilers, the XCG-16 could deploy them to reduce lift and increase drag, enabling rapid descent and short landings on various terrains. Additionally, the glider was equipped with retractable landing gear, deployable for landings on rough ground. The maiden flight test of the MC-1 began on the 19th of July 1943 at March Field, California. The first test run proved to be a success and was commended by military and business observers. A second test flight was scheduled at March Field on the 11th of September 1943, but this run ended in disaster. Among the crew and passengers aboard the glider were notable aviator and businessman Richard Chichester DuPont and military glider specialist Colonel Ernest Gable, who was set to pilot the MC-1 for its demonstration. During the demonstration, the glider was towed by a Lockheed C-60. Shortly after takeoff, an unintended encounter with the C-60's prop wash caused the glider to violently sway from side to side. Compounding the issue, the weight ballast inside the glider had not been properly secured and began to shift, exacerbating the rapid tilting of the XCG-16. Recognizing that a crash landing was imminent, 3 of the passengers, including DuPont, attempted to parachute from the glider as it continued its descent. While 2 passengers successfully landed safely, DuPont tragically lost his life when his parachute didn't open in time. Colonel Gable remained on the glider and also lost his life when it ultimately crashed into the ground. Despite the tragic setback at March Field, Bolus continued with the design and the US military awarded a contract to the General Airborne Transport Company in November 1943 after negotiations. The contract approved the construction of 3 MC-1 units. 2 flyable and 1 for static tests were awarded by the USAF. The completed full-sized MC-1 gliders were also given the military designation XCG-16 and the name stuck. Only 1 completed XCG-16 unit was manufactured and submitted for USAC testing. test pilots and engineers acknowledged the XCG-16's strong aerial performance, highlighting its excellent stability and maneuverability. However, military observers concluded that the glider fell short of expectations in terms of cargo and loading capabilities, deeming it unsuitable for combat situations. Consequently, no additional units were produced. There was initial consideration of repurposing the glider for new Air Force experiments. In 1944, the US military explored the concept of extending the range of existing transport and bomber aircraft by utilizing trailing gliders to carry fuel. The XCG-16 airframe was handed over to the Cornelius Aircraft Company, known for building gliders, to modify and test the forward-swept wing design, capitalizing on the XCG-16's robust capabilities. The Cornelius Company made several alterations to the glider, renaming it the XFG-1 and prepared it for a test flight. However, the first XFG-1 model crashed during a demonstration in October 1944. Although a second model was produced by Cornelius following the bolus format, by that time the US military had lost interest in the project, leading to the discontinuation of further development.
Aviation, the art of aeronautics, began with the dreamers, inventors and daredevils who dared to defy gravity. The journey of aviation was nurtured by pioneers like the Wright brothers, whose first flight marked a historic milestone. The role of aircrafts in world wars was groundbreaking, dramatically changing warfare strategies. This initiated a technological evolution in aviation, transforming the simplistic wings of a biplane into the thunderous roar of jet engines. Let's journey through the ages of aviation. Behind every great aircraft, there were great minds. These visionaries, like Sir Frank Whittle, the innovator of the turbojet engine, redefined air travel. Then there's Skunkworks Kelly Johnson, the genius behind the SR-71 Blackbird. His designs combined speed, stealth and power, crafting machines that dominated the heavens. The contributions of these pioneers have left an indelible mark on the canvas of aviation, shaping the course of history and inspiring generations of engineers and aviators. Each epoch in aviation history gave birth to extraordinary aircrafts, each with their own unique features and roles. The Lockheed SR-71 Blackbird was a marvel of speed and stealth. The F-105 Thunderchief, a supersonic fighter bomber, was vital in the Vietnam War. The P-51 Mustang, a long-range fighter, was critical in World War II. The P-47 Thunderbolt, a heavyweight fighter, was used extensively in the same war. The A-10 Thunderbolt II, the Warthog, is a close air support icon. The Messerschmitt Me-262 marked a leap forward in aviation technology. Each of these game changers were instrumental in their eras, and their legacies still resonate today. Beyond the game changers, there are those that have transcended their practical roles to become icons. The Concorde was not just an aircraft, it was a supersonic symbol of luxury and speed. The B-52 Stratofortress, a strategic bomber, is an icon of power and resilience. These magnificent machines and others like them have become much more than just aircrafts. They are enduring icons that encapsulate the audacious spirit, the relentless innovation, and the boundless ambition that define the world of aviation. For more amazing aerial footage, and to join us in this incredible journey, check out the DroneScapes YouTube channel.
The only reason for an airplane to exist is to go fast. At the Great Air Meet in Rheims, Glenn Curtis set a world's record of just over 43 miles an hour, and the quest for speed was on. In 1913, Maurice Prévost was flying a streamlined Dépôt-Dessin monoplane at 126 miles an hour, and Europe claimed the lead in aviation speed. Immediately after World War I, quest for speed became a catalyst for the development of fighter planes. Countries which had not invested in new engines for their wartime fighters would, for reasons of national pride, invest in new engines to race them eastward. Then, in America in the 1930s, the situation reversed itself. Civilian aircraft, like the Travel Air Mystery Ship and the GB, Waddell Williams racers, became even faster than military aircraft. The reason was simple. Same engines were available to both civil racers and military fighters. The fighters had to carry guns, bombs, oxygen, and radios, while the racers were built only for speed. The world's absolute speed record was passed from country to country. And as the racers became faster and more powerful, they also became more expensive. America's Howard Hughes could afford to build his own racer, and with it set a land-plane speed record. But the absolute speed record of 440 miles an hour was set by a Macchi MC-72 seaplane in 1934, financed by the Italian government. Then military aircraft came back into the lead as the Heinkel and Messerschmitt firms competed for the title. Messerschmitt Bf-109R set a speed record of 469 miles an hour in 1939, a record that lasted for many years. When the jet aircraft came out, speed records rapidly accelerated, the British breaking 1,000 miles an hour in 1956 in a Fairey Delta II. Speeds continued to climb, finally reaching 2,193 miles an hour in 1976 by the Lockheed SR-71, alias Blackbird. While speed was the object, there were many other benefits in creating ever faster aircraft. Improvement in fuels, streamlining, lubricants, materials, and the list goes on. Speed produced not only prestige and pleasure, but also utility. The speed record setters ultimately paved the way for commercial transports, business jets, and private planes.